Hello there and welcome to Physics with William, where curiosity is allowed to slow down, difficult ideas are explained without hurry, and science takes the long way around so that even the strangest parts of reality can begin to feel familiar. Tonight, we're going to explore dimensions, beginning with the simplest kind of space that mathematics can describe, and moving gradually toward ideas so large that ordinary words such as place, movement, body, history and universe may no longer mean quite what they usually do. You've probably heard dimensions discussed in several different ways. At school, they may have appeared as length, width and height. In physics, time is often added to the description, giving every event both a location and a moment. In science fiction, dimensions are frequently treated as hidden worlds, alternative timelines, or convenient doorways through which someone can disappear just before having to explain what is happening. All of these uses are connected by one broad idea, although some are far more firmly grounded in mathematics and physics than others. A dimension describes an independent direction, coordinate, or freedom needed to locate something, or describe how it can change. Adding another dimension does not simply make a world larger. It gives that world a new kind of possibility that was unavailable before. Before we go any farther, take a moment to notice where you're listening from tonight. Perhaps you're lying in bed with the room darkened, sitting on a sofa after a long day, or listening through headphones while trying to find a comfortable position that you were certain you had discovered 5 minutes ago. Where in the world are you right now, and what time is it for you? The answer places this moment within several familiar dimensions. Your position on Earth gives us part of the where. Your height above the ground gives us another part. The time on your clock tells us when this particular event is taking place. Someone else may be listening on the opposite side of the planet, in a different room, under a different sky, and at a different hour. Yet both of you are receiving the same sequence of words. Each listener occupies a unique location in space, and a unique moment in time, and that simple fact already shows how dimensions organize experience. They tell us not only that something exists, but where it exists, when it exists, and what kinds of movement are available to it. If you find this journey relaxing, interesting, or simply helpful company while you settle down, you may like the video and subscribe to the channel. It helps this quiet corner of science reach other people who enjoy large questions delivered without alarms, flashing graphics, or someone announcing that the universe will shock you in the next 30 seconds. There will be plenty of surprising ideas ahead, but they do not need to be rushed. Dimensions are easier to understand when we build them carefully, beginning with objects that seem almost too simple to discuss, and then watching what changes each time a new direction becomes available. By following that order, we can separate strict geometry from physical theory and physical theory from speculation. A point, a line, a plane, and ordinary space can be defined precisely. Spacetime belongs to modern physics and has been tested with extraordinary accuracy. Ideas involving branching histories, alternative laws of nature, and every logically possible universe are more uncertain and often serve as conceptual extensions rather than confirmed descriptions of reality. We can still explore them, but we should know when we have moved from measured science into structured imagination. The easiest way to understand dimensions is to think in terms of freedom. Imagine that you are standing in an empty room. You can move from one side of the room to the other. You can walk toward the door or away from it. You can also move upward or downward, although most of us require stairs, a lift, or a moment of poor judgment involving a chair to make much progress in that direction. These three independent ways of moving correspond to the three spatial dimensions of ordinary experience. They may be named in different ways, but the labels do not matter. We can call them left and right, forward and backward, and up and down. We can describe them using the directions of a map or the walls of a building. The important point is that each direction adds a freedom that cannot be produced entirely from the others. Walking forward and sideways does not cause you to rise through the ceiling. Moving upward and forward does not automatically take you sideways. Each dimension contributes something new. Now imagine removing one of those freedoms. Suppose there were no up and no down, not merely because gravity held everything to the floor, but because those directions did not exist. The world would not be a very thin version of our own. It would be perfectly flat with no thickness at all. Every object would be spread across a surface. Every body, building, road, and boundary would have length and width but no depth. A creature living there could move in two independent directions, yet it could never step above or below anything. A closed shape would become a complete prison because there would be no third direction through which to escape. From our three-dimensional viewpoint, however, that prison would not seem secure. We could reach toward the flat world from above, lift the trapped creature away from its surface, move it across the boundary and place it outside. The creature might believe it had vanished from one location and appeared in another. We would know that it had simply moved through a direction unavailable to it. This relationship between lower and higher dimensional observers will guide everything that follows. A higher dimensional being does not necessarily break the rules of the lower world. It may simply use a direction that the lower observer cannot perceive or enter. Think of a locked room drawn on a sheet of paper. A small figure inside the drawing cannot cross the surrounding line without passing through the wall. You can touch any point inside the room directly because your hand approaches from outside the plane of the paper. The boundary is complete within 2 dimensions, but incomplete from a 3-dimensional viewpoint. In the same way, the walls around you appear to enclose your body because you move within 3 spatial dimensions. If another spatial direction existed, and a being could use it, that being might enter the room without crossing the floor, ceiling, walls, windows, or door. It might reach inside a sealed container without opening it. It could perhaps see the internal structure of your body without looking through your skin, just as you can see the entire interior region of a flat drawing without cutting through its boundary. These examples sound impossible because we instinctively treat the directions available to us as the complete set of directions that can exist. That instinct is understandable. The human brain developed to navigate ordinary environments, recognize faces, judge distances, avoid falling objects, and remember where useful things had been left. It did not develop to form direct mental pictures of a 4th spatial direction. Our imagination depends heavily on experience, and every object we have ever seen has appeared within 3-dimensional space. We can rotate a cube in our minds because we have handled solid objects. We can picture a square because we have seen flat surfaces. When asked to imagine a direction that is not left, right, forward, backward, up, or down, the brain often responds by quietly reusing one of the directions it already knows and hoping nobody notices. This limitation does not prevent us from reasoning about higher dimensions. It only means that analogy becomes more useful than direct visualization. We can study how a 3-dimensional object would appear to a 2-dimensional observer, and then use the pattern to think about how a 4-dimensional object might appear to us. Suppose a ball passed slowly through a perfectly flat world. The inhabitants would not see the whole ball. At first, they would see nothing. When the surface of the ball touched their world, a point would appear. That point would become a small circle. The circle would grow as wider sections of the ball passed through, reach its largest size near the middle, then shrink until it returned to a point and vanished. The flat observers would experience a changing 2-dimensional object. We would understand that each circle was only a cross-section of one 3-dimensional ball. If a 4-dimensional object passed through our space, we might experience something similar. We would see only a changing 3-dimensional section. An object could appear from nowhere, grow, change shape, split into separate pieces, join with itself, expose internal regions, and disappear without moving away in any familiar direction. None of this would require the complete object to be created or destroyed during the event. The changing form would reflect the portion intersecting our space at each moment. This does not mean four-dimensional objects are regularly moving through kitchens and avoiding detection behind the kettle. It means that, mathematically, a lower dimensional observer receives only partial information about a higher dimensional structure. The same idea becomes especially important when we begin to discuss time. You normally experience your body as something that exists in the present moment. It has a current shape, age, position, and condition. Yesterday's body is remembered, and tomorrow's body is anticipated, but neither appears directly beside the one you have now. When time is treated as part of space-time, however, a person's existence can be described as an extended history rather than as a single body repeatedly replaced by later versions. Your infancy, childhood, present condition, and old age may be understood as different temporal sections of one larger structure. From within ordinary experience, you pass through those moments one at a time. From a hypothetical viewpoint outside that sequence, an entire life might be visible at once, much as an entire road is visible on a map, even though a traveller experiences it one location at a time. This shift changes the meaning of an object. A circle may be a section of a sphere. A body at one moment may be a section of a complete life. A particular history may be one route through a wider set of possible histories. As dimensions are added, the object we first considered complete becomes part of something larger. The lower dimensional observer is not necessarily wrong about what it sees. Its observation is incomplete because its viewpoint reveals only a slice. This is a useful habit of thought well beyond geometry. Human beings regularly assume that what can be observed from our position must represent the whole of reality. Dimensions remind us that a limited view can be accurate without being complete. The word dimension is sometimes stretched too far, so it is worth setting careful expectations before moving upward. The first few dimensions in our journey are geometric. A point has no spatial extension. A line has one dimension. A plane has two. Ordinary space has three. Time enters physical descriptions in a different but closely related way, producing space-time rather than simply another direction through which we can wander at will. Beyond that, we will use a common conceptual ladder in which additional levels represent access to different timelines, different initial conditions, different laws of physics, and eventually every internally consistent form of reality. This ladder is not a universally accepted scientific map of literal dimensions. It is a framework for exploring how each new level might contain complete structures that lower levels experience only one piece at a time. Keeping that distinction clear does not make the later ideas less interesting. It makes them more useful. We can ask what would happen to individuality if every possible version of a life were visible at once. We can ask whether movement would still mean changing location, or whether it might mean selecting between histories. We can ask how a universe with different physical laws could be compared with our own, and whether every imaginable universe is genuinely possible, or whether logical consistency places firm limits on what can exist. The farther we go, the more familiar concepts begin to weaken. A human body becomes a temporary section of a larger pattern. A decision becomes a branching point among possible histories. A universe becomes one case within a broader collection. At the highest conceptual levels, even the distinction between something existing and not existing becomes difficult to state without first deciding what we mean by possibility. For now, remain with the ordinary room around you. Notice that its shape depends on dimensions. A wall is not merely a collection of material. It extends in certain directions and forms a boundary because space allows those directions. A doorway works because it creates an opening across the wall's surface. A cup can hold water because its three-dimensional structure encloses a volume. Your body can contain organs because one part can be separated from another, while remaining connected through vessels, tissues, and nerves. Almost every familiar property of an object depends on the dimensional space it occupies. Remove one spatial dimension, and the structure changes completely. Remove another, and almost everything recognizable disappears. A two-dimensional creature could not have a digestive system arranged like ours, because an internal tube running from one opening to another would divide its body into separate pieces. A one-dimensional creature would face even greater restrictions, because every part would need to lie along a single line. One part could block access between all the others. In 0 dimensions, there would be no separate parts at all. Biology, movement, and internal structure would become impossible in their familiar forms. Each reduction removes freedoms so basic that lower dimensional life would need to be imagined in entirely different terms. Moving upward creates the opposite effect. Additional dimensions may allow structures that seem impossible from below. A higher dimensional organism, if such a thing could exist, might possess connections that pass around every obstacle in our space. It might inspect internal regions directly. It might appear as several separate bodies, while remaining one connected object in a direction we cannot see. These are geometric possibilities, not observations of real creatures, but they demonstrate how strongly dimensional limits shape our idea of what an object can be. There is also a quieter point to consider. A being does not normally feel that it lives in an incomplete reality. A flat creature would not wake each morning frustrated by its lack of height, unless it had somehow learned that height existed. It would build its science, language, and common sense from movements available within the plane. A one-dimensional creature would treat forward and backward as the complete geography of existence. A point, if awareness could somehow be assigned to it, would not experience itself as confined to one location, because the idea of another location would have no meaning within its world. We may be in a similar position. Our 3 spatial dimensions feel complete, because they support every movement we have ever performed. Time feels as though it flows in one direction because memory records the past, and anticipation points toward the future. We experience one version of history, one set of physical laws, and one observable universe. It is natural to call that collection reality. The dimensional staircase asks whether reality may contain structures that our position reveals only partially, just as the flat world reveals only circular sections of a passing ball. There is no need to believe that every proposed level physically exists in order to benefit from the exercise. The journey teaches us how perspective limits description. It shows how objects change when new freedoms are introduced. It separates size from dimension, movement from change, and local experience from complete structure. It also gives us a disciplined way to approach ideas that would otherwise sound like a loose collection of science fiction claims. At every stage, we will ask the same questions. What positions are available? How can something move? What can an observer detect? What would remain hidden? Does the idea come from established mathematics, tested physics, speculative theory, or metaphor? Those questions will prevent us from confusing an interesting model with a confirmed discovery. They will also help when intuition begins to fail, which it will. Higher dimensions are not difficult because they require complicated language. They are difficult because the ordinary meanings of simple words stop working. Inside may no longer be separated from outside. Before and after may become parts of one complete structure. A single person may become a collection of possible histories. A universe may no longer mean everything that exists. The most reliable way forward is to begin with almost nothing. We should not start with infinity, alternative physical laws, or an endless collection of universes. We should remove the room, the walls, the objects, and every direction of movement. We should begin with one location that has no length, no width, and no depth. It is not a tiny ball and not a grain of matter. It has no surface, no interior, and no direction in which it can turn. There is no distance across it and no second place within it. It marks a position without occupying an area or volume. That is the zeroth dimension. It appears too simple to contain anything worth discussing, yet it forms the starting point for every shape and every higher dimensional structure that follows. Once we understand what it means for a point to have a position but nowhere to go, we can give it a single direction, allow distance to appear, and watch the first possible movement enter reality. At the beginning of this journey, all ordinary space has been removed. There is no room, no floor, no ceiling, and no distance separating one place from another. What remains is a point, the simplest object that geometry can describe. A point has a position, but it has no length, width, or depth. It does not occupy a tiny amount of space. It occupies no space at all. The dot we draw on paper is only a visible marker for the idea because every real mark has some thickness and area. Even the finest pencil point leaves graphite spread across a small part of the page. Under a microscope, that neat little dot would become an uneven landscape of material. A true geometric point would not become larger under magnification because there is nothing across it to enlarge. It has no surface, no edge, and no interior. It tells us where something is without providing any room for anything to be inside it. This difference between a point and a very small object is essential. A grain of sand may be tiny, but it still has length, width, and depth. A bacterium may be too small to see without equipment, yet it still has a body with internal regions. An atom is smaller still, but it exists within three-dimensional space and has physical properties that extend across that space. Shrinking an object does not reduce its number of dimensions. A small cube remains three-dimensional no matter how small it becomes. To produce a zero-dimensional object, we must do more than reduce size. We must remove every direction in which the object could extend. The result is not the smallest possible ball. It is something with no shape at all. Shape requires parts to occupy different positions. A circle has points arranged around a centre. A square has corners and sides. A sphere has a surface surrounding a volume. A point cannot have a shape because it contains no separate locations. There is no left side of a point and no right side. There is no upper region and no lower region. Turning it makes no difference because it has no orientation. A coin looks different when viewed from the side than when viewed from the front, but a point has no side or front to reveal. It cannot be upside down, sideways, or badly positioned on a shelf. It can only be located. Movement is equally impossible within a zero-dimensional world. Movement requires at least two distinct positions. An object begins in one place and later occupies another. Inside a point, there is no second place available. A being restricted to a point would not be trapped in the same way that a person can be trapped in a room. A room contains many possible positions even when the door is locked. You can stand near one wall, move toward another, sit on the floor, or pace in a manner intended to suggest calm while achieving the opposite. The point offers no such possibilities. It has no walls because walls require extension, but it also has nowhere beyond its current location that can be reached from within its world. This is why the zeroth dimension represents no spatial freedom. In one dimension, movement will become possible in two opposite directions along a line. In two dimensions, a new direction will allow movement around obstacles. In three dimensions, another direction will allow movement above or below a surface. At zero dimensions, none of these freedoms exist. There is position without travel and location without distance. The point is not choosing to remain still. Stillness normally means that movement could happen, but does not. In a zero-dimensional space, movement is not an available condition in the first place. Trying to imagine a creature living in such a world quickly exposes how dependent life is on spatial structure. A living body contains many parts arranged in different places. Cells have boundaries separating their interiors from their surroundings. Organs occupy distinct regions while remaining connected. Nutrients move through passages. Signals travel along nerves. Muscles change shape. Even the simplest known forms of life rely on molecules being arranged in particular patterns and interacting across small distances. A zero-dimensional body could have no internal arrangement, because every part would have to occupy the same indivisible location. It could not possess a mouth, a stomach, a brain, or any other structure requiring one region to differ from another. a zero-dimensional being could not look outward either. Vision requires light to travel from a source, reflect from an object, and enter a sensory system. Hearing requires vibrations to move through a material. Touch requires one physical surface to meet another. None of these processes can occur without spatial separation and movement. If awareness was somehow assigned to a point, it would not experience a surrounding darkness, because darkness still suggests an empty region around the observer. There would be no surrounding region. It would not see blackness in every direction because there would be no directions in which to look. The absence of space is not the same as an empty space. That distinction is easy to miss because the imagination tends to place the point inside a larger setting. We picture a tiny dot floating against a dark background, perhaps with a generous amount of empty room around it. Yet the background already introduces space. It gives the point an outside, a surrounding area, and possible directions. A genuinely zero-dimensional universe would not be located inside anything larger. It would not float in a void because a void still has extension. Asking what lies beside it would assume that beside is a meaningful direction, but no such relation exists there. A point can still be part of a larger space, of course. The center of a circle is a point within a plane. The corner of a cube is represented as a point within three-dimensional space. A city may be marked as a point on a map, even though the real city extends for many miles and contains a remarkable number of roads that become confusing precisely when one is already late. In these examples, the point identifies a location inside a larger structure. The zeroth dimension becomes more difficult when the point is not merely inside the world, but is the entire spatial world. If time is also absent, nothing can change. There can be no earlier state and no later state. The point does not wait because waiting requires duration. It does not remain unchanged for a long time because there is no long time through which it could remain. It simply exists as one complete spatial fact. Language struggles here because most verbs imply time. To happen, continue, pause, begin, or end all require a sequence. A world with no space and no time would not contain an event in the usual sense. It would be a single condition without before or after. If time is allowed while space remains zero-dimensional, the situation becomes slightly richer. The point still cannot move because it has no alternative spatial location, but its state could change from one moment to another. It might have one property and later have another. A simple scientific model may treat a system as zero-dimensional when its position is irrelevant, but its behavior over time matters. For example, a model might track the temperature of a well-mixed container while ignoring differences between one part of the container and another. The real container has size, but the model treats the system as though one value describes the whole thing at each moment. This is common in physics. Scientists often treat objects as points when their internal size does not matter for the problem being studied. A planet may be represented as a point while calculating its path around a star. The planet has a diameter, atmosphere, mountains, oceans, and enough local weather to complicate many holidays, but those details may be unimportant when the distances involved are enormous. Representing the planet by a point allows the calculation to focus on its position and motion. The same method can be used for a moving vehicle, a falling object, or a satellite. The object is not literally zero-dimensional, it is being simplified. A point model says that all relevant information about location can be assigned to a single position. This does not deny the object's size. It temporarily ignores that size because including it would add detail without improving the answer. Maps rely on similar simplifications. A railway station may appear as one dot even though the actual station contains platforms, staircases, ticket barriers, shops, and at least one person standing directly where everyone needs to walk. The dot is useful because it tells us where the station is relative to the rest of the route. It does not try to reproduce the entire building. A point can carry meaning without containing the thing it represents. This gives the point an important role in geometry and science. It marks the location where something begins, ends, crosses, or changes direction. The endpoints of a line segment are points. The corners of a polygon are points. The center of a circle is a point. The location of an event can be represented as a point in space and time. Although a point has no size, it helps define structures that do. A lane is described through the set of points lying along it. A surface can be understood as a collection of locations arranged in two independent directions. A volume contains points distributed through three spatial directions. This can sound as though larger objects are built from points in the same way that a wall is built from bricks, but the comparison is not exact. Bricks have size and contribute their widths to the wall. A point has no length to contribute. Mathematics describes a continuous line through an unbroken set of positions rather than through a row of tiny beads. Between any two different points on a line, another point can be identified. Between either of those and the new point, another can be found. This process has no final smallest gap. No matter how closely we look within the mathematical line, additional positions remain available. The line is continuous rather than assembled from a limited number of indivisible spatial blocks. The point therefore has almost no internal complexity, but its relationships with other points allow complexity to appear. One point alone provides only a location. Two distinct points allow separation to be discussed. Several points can define corners, paths, or patterns. An enormous set of points can describe a smooth curve or a surface. The point does not change as the surrounding structure becomes richer. What changes is the number of relationships available. This is an early example of a pattern that will continue as we move into higher dimensions. A lower dimensional object may be simple by itself, yet become part of something much larger. A point can be an endpoint of a line can be an edge of a square can be a face of a cube. The lower dimensional object does not disappear when a higher dimension is added. It becomes a boundary, section, or component of the new structure. From the viewpoint of a one-dimensional creature, a point may act as a barrier. Imagine a being that can move only along a line. If a point blocks that line completely, the being cannot go around it because around requires another direction. From our higher dimensional viewpoint, we could move the obstacle off the line. The creature could not even describe that action using its ordinary spatial language. The point, which appears almost powerless in isolation, can become a complete obstruction within a one-dimensional world. A point can also be the only visible part of a higher dimensional object. If a line were to pass through a zero-dimensional world, the world would contain only the location where the line intersected it. There would be no way for an observer confined to the point to detect the line's length, because that length extends beyond the available space. The larger object would be reduced to the part that fits within the lower dimension. This idea becomes easier to understand in the next levels. A flat observer sees only a changing cross-section when a solid object passes through its plane. We might see only three-dimensional sections of a four-dimensional object. The zero-dimensional case gives the simplest version of that rule. Whatever larger structure passes through the point can be detected only at that single location. The point also forces us to separate existence from size. In everyday speech, something that takes up no space may sound like nothing. Mathematics treats the two differently. Nothing has no defined location or properties. A point has a precise role. It may be identified, compared, placed within a structure, and used to describe relationships. It has no extension, but it is not absent. An empty place and the absence of a place are not the same. An empty chair is a location where nobody is sitting. If the chair does not exist, there is no seat to occupy. In a similar way, a point defines a location even though it contains no area or volume. It provides the where without providing a region. This difference matters in physics because a property may be assigned to a point. We can speak about temperature at a location, density at a location, or the strength of a field at a location. The value is not a tiny object stored inside the point. It is information associated with that position. By assigning values to many points, physicists describe how conditions vary across space. A weather map does this in a practical way. Each location can be associated with temperature, pressure, humidity, and wind. The entire pattern emerges from values distributed across many positions. A single point does not contain the weather system, but it can tell us what conditions apply there. A field in physics works through a related idea, assigning a quantity or direction to every point in a region. Fundamental particles are also often described as point-like. This means that experiments have not revealed a measurable internal spatial structure for certain particles at the scales currently accessible. It does not mean that physicists have photographed a perfect mathematical dot. It means the point description is consistent with observations and works well within the relevant theory. Other particles do have measurable internal structure. Protons and neutrons, for example, are not treated as featureless points in every context. They contain smaller constituents and have spatial extent. The word point-like must therefore be used carefully. It describes what a model or experiment can resolve, not necessarily the final nature of reality. The point should not be confused with a singularity either. In discussions of black holes, the word singularity is sometimes presented as though all matter has been crushed into a zero-dimensional dot. The actual physics is more cautious. A singularity indicates that the equations of general relativity reach a limit where familiar quantities become undefined or grow without bound. Many physicists expect a more complete theory to alter that description. A geometric point is a clean mathematical object. A gravitational singularity marks a problem at the edge of a physical theory. This distinction between mathematics and physical reality will remain important. Geometry can define perfect points, perfectly thin lines, and perfectly flat planes. Physical objects are never drawn with absolute perfection. A wire has thickness, a sheet has depth, a mark has area. The mathematical ideal is still useful because it isolates the property we wish to understand. The point isolates location from size. Once that idea is clear, we can ask what must be added to create distance. One point alone cannot define a direction. A second distinct point introduces a relation. We can say that the two positions are different. With a continuous set of positions extending between and beyond them, a line appears. The first dimension does not give us a complicated world. It gives us only one path. An inhabitant can move one way or the opposite way, but it cannot turn aside. Every object shares the same narrow route. There is no room to pass, no way around an obstacle, and no hidden region beside the line. Compared with the point, this is an enormous increase in freedom because movement has become possible. Compared with our world, it remains severely limited. The transition begins by allowing the point to occupy more than one possible location. It can remain where it is, move toward one direction, or move toward the other. Distance can now be measured between positions. Order becomes meaningful because one point may lie between two others. The world gains extension without gaining width. A point that had nowhere to go now receives a path, but the path permits no deviation. Every journey follows the same line, every meeting blocks the route, and every possible destination lies either ahead or behind. Once that single direction is available, the quiet point becomes the foundation of a one-dimensional world where movement exists for the first time, though choice remains narrower than any traveller in our space would find comfortable. Once a point is given one possible direction of extension, the first dimension appears. The point is no longer the entire world. It becomes one position among endlessly many positions arranged along a line. For the first time, distance exists. One location can be nearer than another, one point can lie between two others, and something can leave where it began and arrive somewhere else. This may sound like a small change, especially from our perspective, but compared with the complete immobility of the zeroth dimension, it is an enormous increase in freedom. A one-dimensional world contains movement, separation, order, and the possibility of a journey. It simply allows all of them to happen along one path and nowhere else. Imagine a perfectly straight line extending farther than any inhabitant could travel. It has length, but no width and no height. It is not a narrow road, a thin wire, or a mark drawn across a page, because all of those have thickness. However fine a hair may seem, it still has a circular surface and an interior. A geometric line has no sides that can be touched, and no surface that can be walked upon. It consists only of positions arranged in a single direction. We can draw it as a stroke of ink to help our eyes, but the mark is only a representation. The true line offers no space above, below, or beside itself. A being living on this line would experience a world divided into two possible directions. It might call them forward and backward, left and right, or perhaps homeward and away from home if its culture had become unusually sentimental. The names would not matter. Every possible destination would lie in one direction or the other. There would be no third option, no turning aside, and no route that curved around an obstruction. If something blocked the line, the path would be completely blocked. This is difficult for us to appreciate because we are surrounded by alternatives. When someone stands in front of us, we can step to one side. When a fallen tree blocks a trail, we may climb over it or walk around it. Even in a narrow corridor, our bodies occupy different positions across the width of the passage, allowing one person to turn, squeeze past, or at least make an awkward attempt while both parties apologize repeatedly. None of these actions would be available in one dimension. There is no sideways, there is no over, there is no underneath, there is only the line. Suppose two one-dimensional creatures approach each other. If their bodies occupy sections of the line they cannot pass, each creature completely separates the world on one side of its body from the world on the other. To exchange positions, one would need to move through the other. One would need to be removed from the line, or the creatures would need some physical process unlike anything in ordinary solid matter. A simple meeting could become a permanent traffic problem. The one-dimensional world would have no roundabouts, no passing lanes, and no helpful side streets suggested by a navigation system after the delay had already become unavoidable. The order of objects along the line would therefore be extremely important. In our world, three people standing in a row can change places by stepping around one another. On a line, their order cannot change unless they pass through each other, or one is somehow lifted into a higher dimension. If one creature stands between two others, it remains between them as long as all three stay on the line and cannot overlap. The middle creature controls contact between the outer two. Messages, materials, and movement may all need to pass through it. This means that the idea of between becomes one of the defining relationships of one-dimensional space. A point may lie before another, after another, or between two others. These relations create a natural order. If several towns existed along the line, a traveller moving from the first town to the fourth might be forced to pass through the second and third. There would be no alternative route. Geography would be simple to draw and difficult to escape. Navigation would require only one coordinate. In our ordinary space, describing a location takes several pieces of information. A street address tells us something about position across a surface, while the floor of a building adds height. On a line, one number would be enough to mark every possible place, provided the inhabitants agreed on a starting location and two directions. A house could be located a certain distance to one side of the origin. Another could be placed farther in the opposite direction. The entire known world could be mapped as an ordered sequence. A one-dimensional map would look very much like the world itself. There would be no need to flatten landscapes or represent winding roads. Every road would be the same road. Every location would lie somewhere along it. A traveller could not become lost by taking a wrong turn because there would be no turns. The traveller could still go in the wrong direction, pass the destination, misunderstand the distance, or confidently continue for several hours after refusing to ask anyone for help. Dimensional simplicity does not guarantee sensible decision-making. The idea of direction becomes clearer if we return to the point from which the line began. In 0 dimensions, a point had a position but no way to leave it. In 1 dimension, the point can move and trace a path. every position it occupies belongs to the same line. Movement becomes measurable because the starting location and ending location can be compared. Speed becomes meaningful when time is included because the point can cover more or less distance during a given interval. A moving point is one of the simplest models in physics. An object travelling along a straight track may be treated as one-dimensional when motion in other directions can be ignored. A train moving between stations, a lift travelling between floors, or a bead sliding along a wire can all be approximated in this way. The actual train has width and height, the lift has a floor and walls, and the bead is a three-dimensional object, but the relevant movement may occur along a single path. This is an example of how dimensions can describe a model without claiming that the real object has been flattened. Scientists often remove unnecessary directions to make a problem easier to study. If a car is travelling along a straight road, and we only care about how its distance changes, treating the motion as one-dimensional may be enough. The model ignores small sideways movements, the shape of the vehicle, and the driver's determined belief that changing lanes every 30 seconds will somehow defeat traffic. One-dimensional models are powerful because they isolate basic relationships. They allow us to examine position, movement, collision, and order without the added complexity of turning in several directions. The line may be simple, but it contains infinitely many possible locations. Between any two distinct points, there are more points. No matter how small the distance becomes, another position can be identified within it. This continuity is very different from a row of separate stepping stones. A row of stones offers a limited collection of places where a traveller can stand. A continuous line offers every intermediate position. There is no smallest required step built into ordinary geometry. A moving point can pass smoothly from one place to another rather than jumping across gaps. The distinction between a continuous line and a sequence of separate points becomes important in mathematics and physics. Some systems are described using continuous positions, while others may be represented as a chain of discrete sites. A creature living on a continuous line could in principle occupy any location. A creature living on a discrete one-dimensional grid might move only from one allowed site to the next, rather like walking along an endless row of tiles without being permitted to stop on the joins. Our focus here is the geometric line, which has no gaps and no thickness. Yet imagining life on it requires more than simply placing familiar animals in a narrow corridor. Ordinary organisms cannot survive as perfectly one-dimensional bodies. Every known form of life depends on the internal structure, and structure requires parts to occupy different positions. A one-dimensional organism could have parts arranged along its length, but this creates severe problems. Consider digestion. In a three-dimensional animal, food enters through an opening and travels along a tube through the body. The digestive tract does not split the animal into disconnected regions because tissues can surround the tube. In a one-dimensional body, a passage running through the organism would occupy the same line as everything else. There is no space around the passage. Any opening or channel could divide the creature completely. The same difficulty affects circulation and nerves. A blood vessel cannot pass beside an organ because there is no beside. Two nerves cannot cross without meeting at the same location. A structure placed in the middle of the body may block all communication between the regions on either side. The organization of a one-dimensional organism would need to be radically different from familiar biology. It might resemble a sequence of functional segments arranged along the line, but even that description borrows too much from three-dimensional anatomy. If the segments are solid and cannot overlap, each one blocks direct contact between all non-adjacent segments. Information would have to pass from one section to the next in order. Damage to a middle section could isolate everything beyond it. A one-dimensional creature would be less like a compact body with interacting organs, and more like a chain in which every link controls access to the next. Reproduction would present its own difficulties. Two organisms could not simply approach, interact, and then move around one another. Their order on the line might become fixed. If one offspring appeared between its parents, it would remain between them unless one body passed through another or left the line. Population growth could fill available regions and create complete barriers. Predators and prey would face a world without escape routes. If a predator approached from one direction and an obstacle blocked the other, the prey would have nowhere to turn. If two predators approached from opposite sides, the result would be especially inconvenient. Camouflage might still help if vision existed, but hiding behind an object would work only from one direction. Every shelter would also be a blockage. These problems show that a realistic one-dimensional ecosystem would require physical rules very different from those governing ordinary matter. It may be more useful to imagine simple agents rather than biological animals. An agent could occupy a location, sense signals arriving from either side, change state and move along the line. It might have no internal organs and no need to eat. Even then, its experience would be shaped by the strict order of the world. What could such a being see? Vision as we know it would be extremely limited. Light would have only two possible directions of travel along the line. An observer could receive signals from one side or the other, but anything behind the nearest object would be hidden completely. In our world, light passes around objects along many paths, and we can move our heads to gain a new angle. In one dimension, there are no angles of view. The nearest opaque object in each direction would block everything beyond it. The visual world might therefore consist of two pieces of information, one arriving from each side. Distance could perhaps be inferred from brightness, travel time, or other properties, but objects could not appear beside one another in a field of view. There would be no panorama, no horizon stretching across space, and no arrangement of shapes across a surface. The observer might know that something is approaching from the positive direction, or receding toward the negative direction, but the rich visual geometry familiar to us would be absent. Sound would face similar restrictions. A vibration travelling along the line could approach from either direction. An obstacle might block or reflect it. The position of a source could be reduced to which side it occupies and how far away it seems. There would be no surrounding soundscape, only signals ordered along one path. The one-dimensional being would also have an unusual relationship with its own body. A creature in 3 dimensions cannot see all of itself at once without mirrors or equipment. A one-dimensional observer might sense only the nearest part of another extended body, because the rest would be hidden behind it along the line. If the observer had a front and a back, each side would reveal only what lay directly beyond the outermost boundary. A higher dimensional observer would have a much more complete view. We could look at the entire line from outside it. Every creature, object, and gap would be visible at once. Nothing could hide behind anything, because we would see the ordering of all positions from a direction unavailable to the inhabitants. Their private spaces would not be private to us. Any barrier that divided the line could be bypassed simply by reaching in from outside and placing an object on the other side. To a one-dimensional creature, this intervention would look impossible. An object could vanish from one position and reappear beyond a barrier without crossing the points between. Two creatures could exchange places without passing through each other. A blocked route could become open without the obstacle moving left or right. The only explanation available within the line might involve creation, destruction, or a violation of causality. From our perspective, we would merely lift the object away from the line, move it through a second spatial direction, and return it. This is the same relationship we previously considered between a flat world and our 3-dimensional space, now reduced to a simpler case. A higher dimension provides a route around barriers that are complete in the lower world. What appears sealed from within may be open from outside. Imagine a short line segment enclosed between 2 endpoints. A creature living within it cannot move beyond those boundaries. For us, the entire segment can be seen at once. We might touch any point directly. We could remove the creature and place it elsewhere without carrying it through the intermediate positions. The creature would have no sensory experience of the path, because the path lies outside its space. This thought experiment introduces a pattern that will become more important with every dimension. A lower dimensional observer experiences a sequence of local events. A higher dimensional observer may see the full arrangement simultaneously. The creature on the line discovers one location after another by travelling. We can view the whole line without making the same journey. The difference resembles the relationship between a traveller and a map. A traveller walking along a road encounters each bend and town in order. Someone looking at a complete map can see the entire route at once. The map is not literally a higher spatial dimension than the road in every sense, but the analogy captures the difference between local experience and a broader view. For the one-dimensional being, movement is the only way to discover distant locations. It cannot step away from the line to inspect its shape from outside. If the line curves through our space, the inhabitants may not notice the curve. Their internal measurements depend on distance along the line, not on how the line appears to us. Picture a long wire bent into a circle. Creatures confined to the wire would experience one-dimensional space. They could move in either direction and eventually return to their starting point. From our viewpoint, the line forms a loop. From their viewpoint, the world may simply be finite, but without endpoints. They would never encounter a wall marking the end of space. Continuing far enough in one direction would bring them home from the other side. This possibility shows that a one-dimensional space need not be an infinite straight line. It could be a finite segment with boundaries, an endless line, or a closed loop. The local experience remains one-dimensional because only one independent direction of movement is available at each location. A creature moving around the loop might attempt to describe the global shape of its world through travel and measurement. It could discover that continuing steadily eventually returns it to the start. It might infer that space is closed. Yet it could not see the circle as we do without access to the surrounding plane. The curvature visible to us depends on a higher dimensional viewpoint. The same idea helps us understand why the shape of a space is not always obvious to those living inside it. We experience our world from within. Large-scale geometry must be inferred through measurements of distances, angles, light, and motion. We cannot simply step outside the universe and look back at its overall shape, much as the line creature cannot leave its loop to inspect it from above. There is another curious case. The one-dimensional world might branch like a railway junction. At a branching point, several paths meet. Locally, however, the junction no longer behaves like an ordinary line because the creature has more than two possible directions. A pure one-dimensional line gives exactly two local directions at each ordinary point. Branching adds a network structure with choices that are not captured by a single smooth line. A network can still be called one-dimensional in some mathematical contexts, because each individual path has length without area, but life at a junction would be very different from life on a simple line. The creature could choose among routes. Different paths might reconnect. The world could contain loops, dead ends, and complex patterns even without acquiring a continuous second dimension. This distinction shows that dimension does not describe every feature of a world. Two spaces may both be one-dimensional while having different global structures. An infinite line, a loop, and a branching network do not offer the same journeys. Dimension tells us how many independent directions exist locally, while topology describes broader properties such as connection, boundaries, and loops. The inhabitants would not use those words at first, but their lives would depend on the differences. A creature on an infinite line could travel forever without returning. A creature on a loop would eventually revisit every location. A creature on a segment would encounter an endpoint. A creature in a network might face choices at junctions, while remaining unable to step into the empty regions between paths. Time would give these worlds history. Without time, the line would exist as a fixed arrangement of positions, but nothing could move along it. With time, objects could change location, collide, separate, and send signals. Each creature would experience events in sequence. The line provides where, while time provides when. It is important not to confuse the direction of time with the spatial direction of the line. A A creature may move forward or backward in space, but it still experiences time proceeding from earlier to later in the usual way. Turning around does not reverse its age. Returning to an old location does not return it to the earlier moment when it first visited. The distinction seems obvious to us, yet it becomes useful when we later treat time as part of a higher dimensional description. A one-dimensional life would therefore trace a history through both space and time. At each moment, the creature occupies a position on the line. Across many moments, those positions form a record of its motion. We may imagine this record as a path showing where the creature was throughout its existence. From the creature's immediate viewpoint, it is always located at one place during one moment. From a broader physical description, its entire history can be treated as one extended structure in space-time. This will become central when we reach the fourth dimension, but the basic idea begins here. A moving point traces a line. A moving one-dimensional body traces a larger pattern through time. The first dimension gives us the earliest form of distance and the simplest possible journey. It introduces order, barriers, neighbours, and the difference between approaching and receding. It also demonstrates how severely movement can be restricted, even when space is continuous and endless. A traveller may have infinitely many possible destinations while still having only two possible directions. From our higher viewpoint, the limitation is obvious. We can see the missing freedom because we possess it. We know there could be a direction beside the line, even though the inhabitants cannot point toward it. We can imagine lifting them out of their world, carrying them around an obstacle, and returning them somewhere they could not otherwise reach. For the inhabitants, the line is not a narrow version of reality, it is reality. Its order seems natural, its barriers seem complete, and its two directions seem sufficient to describe every possible location. They may develop sophisticated ways to measure distance and motion without ever forming a direct picture of width. The next change will not make the line longer, it will add a new independent direction. Every point on the line will gain an entire line of possible positions beside it. Barriers that once divided the whole world will become objects that can be walked around. Creatures will be able to pass one another, paths will cross, and shapes will enclose regions. The world will gain width, but no thickness, and its inhabitants will discover that freedom in two directions creates possibilities that life on a single line could never contain. The moment a second independent direction is added, the line becomes a plane. A creature is no longer restricted to moving only forward or backward. It can now move sideways as well, although sideways would not feel like an unusual direction to anything born in that world. It would simply be part of ordinary space. Every location could be reached through some combination of movement across the plane, and obstacles that once blocked the entire universe could now be approached from another route. Two travellers could pass one another, a path could bend around a barrier, several roads could connect the same places. The difference between 1 and 2 dimensions is not merely that the world has become wider. A completely new category of movement has appeared, bringing with it shapes, enclosed regions, angles, surfaces, maps, and forms of life that would have been impossible along a single line. A two-dimensional world is perfectly flat. It has length and width, but no thickness at all. It is not the same as a very thin sheet of paper because paper still has a front surface, a back surface, and a small depth between them. A true plane has no upper side and no lower side. Nothing can rise above it or sink beneath it, because those directions do not exist within the world. When we draw flat shapes on paper, we are using three-dimensional material to represent an ideal two-dimensional space. The ink has thickness, the paper has fibres, and the table beneath it is inconveniently solid. The mathematical plane removes all of those physical details and keeps only two independent directions. Imagine an inhabited flat world stretching without thickness in every direction. Its residents might move north and south, east and west, or use any other pair of directions they preferred. Unlike the creatures of the line, they could turn around obstacles rather than waiting for them to move. They could build networks of roads, arrange settlements beside one another, and create boundaries enclosing private regions. A wall would be a line rather than a surface. A house might appear as a closed outline surrounding an interior area. If every part of the wall remained unbroken, the interior would be completely sealed from any creature confined to the plane. This is where the advantages of the second dimension also create new limitations. In one dimension, a point could divide the world. In 2 dimensions, a line can form a barrier. A long wall may be avoided by travelling around one of its ends, but a closed wall creates an enclosure with no available route through or around it. There is no possibility of climbing over the boundary because over would require a third direction. There is no tunnel beneath it because beneath does not exist. A locked room in a flat world would be more secure than almost any room in ours, provided the wall had no gaps and the material could not be broken. From our position in 3-dimensional space, however, the enclosure would not look secure at all. We could see the entire interior from above, reach directly into it, pick up an object, and place that object outside without crossing the wall. The flat inhabitants would witness something that violated every ordinary rule of movement. The object would disappear from the sealed room and reappear beyond the boundary. No opening would be used, and no path through the plane would connect the 2 positions. What looks like impossible transportation from within the flat world would be a simple movement through a direction the inhabitants cannot perceive. A visitor from our space could perform many actions that would appear equally impossible. We could enter a sealed house without opening its wall. We could remove an object from the centre of a locked container without touching the boundary. We could rearrange the internal parts of a flat machine while leaving its outer edge intact. We might lift one inhabitant out of the plane, rotate it, and return it with its left and right sides reversed. To the visitor, this would be ordinary handling. To the resident, it might look like magic performed by someone with a rather alarming disregard for personal space. The flat observer would also struggle to see us as complete objects. If a 3-dimensional object passed through the plane, only the cross-section touching that plane would be visible. Consider a sphere moving slowly through the flat world. Before contact, the inhabitants would detect nothing. When the lowest point of the sphere touched their space, a single point would appear. As the sphere continued through, the point would expand into a small circle. The circle would grow wider, reach its largest size when the middle of the sphere crossed the plane, then shrink again until it became a point and vanished. The inhabitants would not see a ball, they would see a circular object changing size. It would seem to appear without arriving from any direction, expand without adding material from anywhere in the plane, then contract and disappear. If the sphere were hollow, the visible cross-section might form a ring rather than a filled circle. If it contained several internal layers, those layers could appear one after another as different patterns. The flat scientists might describe the event with great accuracy, while remaining unaware of the complete object responsible for it. A cube passing through the plane would create a different sequence of cross-sections. Depending on its orientation, it might first appear as a point, then become a small polygon, change its angles and size, and finally disappear. A more complicated object could produce sections that divide, join, or transform in unexpected ways. What looks like several separate objects in the plane might belong to one connected body extending through the 3rd dimension. A single 3-dimensional ring, for example, could intersect the plane in 2 separate regions. The residents might believe they were observing 2 unrelated objects, while we could see that both were parts of one structure. This matters because perception is shaped by what fits inside the observer's space. A flat being cannot see the whole of a 3-dimensional object at once. It receives only the portion that intersects its world. Even if the visitor speaks, moves, and interacts, the observer has access to a changing slice rather than the complete source. The same principle raises an uncomfortable question for us. If an object with an additional spatial dimension intersected our space, we might see changing 3-dimensional sections without ever perceiving the complete object. A 4-dimensional visitor could appear as an object that emerges from nowhere, changes shape, reveals internal regions, separates into several pieces, joins together again, and vanishes without travelling away. These changes might not reflect the visitor transforming in its own space. They might simply show different sections passing through ours. Just as the flat observer mistakes a changing circle for the whole sphere, we might mistake a sequence of changing volumes for the entire higher dimensional object. The two-dimensional world gives us the clearest way to understand this relationship because we can view the entire plane from outside it. Imagine a flat creature shaped like a closed outline with its organs arranged inside. Another flat observer could not see those internal structures directly, because the creature's outer boundary would block the view. We, looking from the third dimension, could see the inside and outside simultaneously. Nothing within the flat body would be hidden behind its skin from our direction of observation. A three-dimensional medical examination often requires images, surgery, or instruments, because our bodies are enclosed volumes. A higher dimensional observer might inspect us as easily as we inspect a drawing. It might see every organ, cavity, and internal surface without looking through the body in any ordinary direction. A sealed safe would offer no privacy. The contents of a closed box would be visible. The hidden side of every object might be as accessible as the visible side. This does not mean higher dimensional beings are secretly inspecting cupboards, although it would finally explain why certain household objects disappear exactly when needed. It shows that hidden and visible are not absolute properties. They depend on the dimensions available to the observer. Something may be concealed from every direction within one space, while remaining exposed from a direction outside that space. Life in the plane would face unusual biological problems. A flat creature cannot simply be a thinner version of a human. Our bodies rely on tubes and channels that pass through three-dimensional tissue without dividing the whole organism. A digestive tract enters the body, runs through it, and leaves through another opening while surrounding tissues keep the body connected. In 2 dimensions, a continuous passage from one side of the body to another would cut the creature into separate pieces. There would be no tissue above or below the passage to hold everything together. A flat organism might therefore have only one opening connected to a branching internal cavity, rather than a complete tube. Food could enter, and waste could leave through the same route, which would make dining arrangements less elegant but geometrically more practical. Circulation would also be difficult because vessels could not cross one another without meeting. In our bodies, blood vessels, nerves, and other structures pass above or below each other. In a plane, every crossing would require a junction, interruption, or special arrangement. Networks in 2 dimensions encounter this restriction often. Roads drawn on a flat map must meet when they cross unless one is represented as a bridge or tunnel, both of which require the 3rd dimension in the real world. Electrical circuits placed on a single flat layer face similar problems when paths need to cross without connecting. Engineers solve this by using additional layers, bridges, or carefully arranged routes. A truly flat civilization would not have the luxury of stacking one connection above another. Its cities could still become complex. Buildings might consist of enclosed regions connected by narrow openings. Streets could form grids, curves, and branching networks. Neighbours could live beside one another rather than being arranged in a single order. Unlike inhabitants of the line, flat residents could change places by moving around each other. They could gather in groups without permanently blocking the world. A crowd would create inconvenience rather than a complete geographical crisis. Vision would also become much richer than it was in 1 dimension. Light could travel across the plane from many directions, allowing an observer to receive information from a range of angles. Yet the flat creature's visual experience would not resemble ours exactly. If its eyes were confined to the plane, it would see the edges of objects rather than surfaces viewed from above. A closed shape might appear as a boundary occupying part of its field of view. The interior would remain hidden unless an opening allowed light to escape. A flat creature looking at a square would not see the full square in the way we do from above. It would encounter the square's boundary from within the same plane. Parts of the outline could hide other parts depending on the observer's location. The creature would infer the complete shape by moving around it, measuring distances and comparing different views. We can glance down at the entire outline at once because our eyes occupy a position outside the plane. This difference resembles the way we understand three-dimensional objects. We never see every surface of a solid object at the same moment from one ordinary viewpoint. When looking at a box, we see some faces while others remain hidden. We move around it or rotate it to inspect the rest. A four-dimensional observer might see our complete three-dimensional objects in a single view, including surfaces and interiors that are mutually hidden from us. A flat world's inhabitants could develop geometry without ever leaving their plane. They could measure angles, areas, distances, and shapes. They could discover circles, triangles, polygons, and curves. They might investigate whether their world is infinite, or whether it has a more complicated global form. Just as a one-dimensional world can form a loop, a two-dimensional world can curve in ways that are easier for us to see from a higher dimension. Consider creatures living on the surface of a sphere. Locally, their world feels two-dimensional. At every location, they can move in two independent directions along the surface. They cannot move directly away from the surface without entering the surrounding third dimension. If the sphere is enormous compared with their everyday journeys, the ground may appear flat nearby, just as the surface of Earth appears flat across a small field. These residents could travel steadily in one direction and eventually return to their starting point. They might discover that paths initially considered parallel behave strangely across large distances. By making careful measurements, they could infer that their space has curvature even if they could not step outside it and view the sphere as we do. Their world would be finite in area but would have no boundary. There would be no edge where the surface suddenly ended. This offers a useful comparison with our own universe. We study space from within it. We cannot stand outside the cosmos and inspect its overall geometry. Instead, physicists measure the paths of light, the distribution of matter, and relationships between large distances. The flat creature on a sphere shows how inhabitants may infer the global shape of their space without directly viewing it from a higher dimension. Not every curved two-dimensional world needs to sit inside a three-dimensional space. Mathematics can describe curvature through measurements made entirely within the surface. The sphere in our imagination is useful because we can picture it, but the deeper properties of the surface do not depend on an outside observer. This becomes important when discussing the curvature of spacetime. A space can have intrinsic geometry that its inhabitants detect through local experiments. The plane can also be folded or twisted when viewed from our world, although its inhabitants may experience those changes differently. Suppose two distant regions of a flat sheet are bent close together in three-dimensional space. To us, the points may be separated by only a small gap through the air. To a creature confined to the sheet, the distance along the surface remains long. Unless the creature can leave the plane, the nearby region remains inaccessible by the shorter external route. If we created a connection between the two regions, the flat inhabitants could travel between places that were previously far apart. They might interpret this as a tunnel through their space. From our viewpoint, we would have joined two nearby points on the folded surface. Similar pictures are often used when explaining wormholes, although real space-time is far more complicated than a sheet bent around in a room. The analogy is useful only if we remember its limits. The extra surrounding space in the picture helps our imagination, but the geometry does not necessarily require the universe to be physically folded into an ordinary higher dimensional room. Models simplify relationships. They should not be mistaken for photographs of what exists. A flat world also changes the meaning of inside and outside. For a closed curve, the plane is divided into an interior region and an exterior region. A creature cannot move from one to the other without crossing the boundary. From above, we see both regions at once. The curve looks like a simple outline. From within, it is a complete wall. Now imagine that a three-dimensional visitor touches the plane with one finger. The inhabitants would see a cross-section of the finger appear as a shape. If the finger moved, the shape would change. The visitor could place several fingers into the plane, producing several separate visible objects, even though all belong to one body. The residents might classify the shapes as independent creatures. They would have no direct evidence that those forms were connected through a body extending outside their world. If the visitor spoke through each contact point, the flat residents might hear several voices that shared information instantly. The shapes could coordinate perfectly because they belonged to one higher dimensional organism. What appeared to be a group could be a single individual. This begins to loosen our familiar definition of identity. Separate visible bodies are not necessarily separate complete beings when the larger connection lies outside the observer's dimensions. The same possibility can be turned toward us. Several objects appearing disconnected in our space might be parts of one structure, connected through an additional dimension. This is a geometric possibility rather than evidence for a hidden organism, but it demonstrates how individuality depends on the scale and viewpoint from which connection is judged. We call two things separate when no path joins them within the space we can access. Rotation provides another disturbing example. Take a flat creature whose body has a clear left side and right side. We could lift it out of the plane, turn it over, and return it. The creature would now be reversed. Every internal feature would appear mirrored. An organ previously on the left would be on the right. From within the plane, there would be no continuous rotation capable of producing this change without deforming or cutting the body. We can perform the same trick with a drawing by flipping the paper, but the drawing itself cannot turn over while remaining strictly within its plane. A higher dimensional rotation accomplishes what lower dimensional movement cannot. In theory, a 4-dimensional rotation could turn a 3-dimensional object into its mirror image without cutting or reflecting it in the ordinary way. The transformation would pass through a direction unavailable to us. For the flat inhabitants, such events would force difficult scientific questions. They could record the appearances, measure the cross-sections, and construct theories describing the visitor's behavior. Some might argue that the shapes were complete objects. Others might suggest an unseen higher structure. Neither group could directly look into the third dimension. Evidence would need to come from patterns that ordinary 2-dimensional processes could not easily explain. This resembles our own position whenever physics suggests dimensions beyond direct perception. Scientists do not accept extra dimensions merely because they sound interesting. A theory must make clear predictions and agree with observation. Hidden directions cannot become scientific simply by remaining hidden. They must affect measurable events in a way that distinguishes the theory from alternatives. The flat world helps us understand the concept without pretending that every imaginative extension is real. We know the third dimension exists because we inhabit it. The plane's residents in the thought experiment do not. Their difficulty gives us a model for our own limits, not proof that a visitor is waiting just outside ordinary space. As movement continues across the plane, something else becomes possible that the line could never support. Shapes can surround areas, paths can loop without retracing themselves. 2 locations may be connected by many routes. Organisms can avoid each other. Cities can spread in several directions, and information can travel through networks with alternative paths. The world gains redundancy. If one road is blocked, another may remain open. If one connection fails, signals may travel around it. This additional freedom makes complexity easier to organize. Yet the absence of thickness still imposes severe restrictions. Nothing can be stacked. One object cannot pass above another. Crossing networks require intersections. Internal systems struggle to avoid dividing bodies. Every enclosed boundary remains absolute to creatures inside the plane. A flat civilization might become highly advanced within those limits. It could study motion, build machines, observe distant objects, and develop mathematics capable of describing dimensions it could not enter. Its scientists might imagine a third direction by analysing the behaviour of impossible visitors, much as we use lower dimensional analogies to think about spaces beyond our own. The step into 3 dimensions would transform nearly every difficulty they faced. Lines that acted as walls would become surfaces with height. Closed curves would no longer imprison because a traveller could rise above them. Vessels and nerves could cross without meeting by passing over and under each other. Bodies could contain tubes, chambers, and complex organs. Objects could be stacked, rotated through new paths, and hidden inside enclosed volumes. For a flat observer, this additional direction would be almost impossible to picture directly. For us, it is the most ordinary feature of reality. We use it whenever we lift a cup, climb a staircase, open a drawer, or place one object on top of another. The impossible direction of the plane is the space in which our entire lives unfold, and entering it will reveal how three-dimensional freedom gives matter the room to build bodies, planets, rooms, machines, and the familiar world we call home. When the flat world receives one more independent direction, the plane becomes space. Length and width are joined by depth, and shapes that once enclosed areas can now enclose volumes. A circle can extend into a sphere. A square can extend into a cube. A closed line that formed an absolute wall in 2 dimensions becomes only the edge of a surface, and a creature is no longer trapped by it because movement above or below the plane is available. This third direction is so familiar to us that it rarely feels like an additional freedom. We reach upward, step around furniture, place books on shelves, open boxes, and move through doorways without pausing to consider that every one of those actions depends on living in 3-dimensional space. The world feels complete because every object we have touched, every room we have entered, and every route we have travelled has existed within the same 3 directions. A 3-dimensional object has volume. It does not merely cover an area, it occupies a region of space with an interior that can be separated from the exterior by a surface. A ball contains space inside its boundary. A cup surrounds a volume that can hold water. A room is enclosed by walls, a floor, and a ceiling. This ability to enclose volume changes what matter can build. In a flat world, a closed line surrounds an area but leaves no route for tubes to pass through a body without dividing it. In 3 dimensions, organs, vessels, nerves, and airways can cross one another by passing above, below, or around. A blood vessel can move over a muscle while a nerve passes beneath it. The digestive tract can run through the body while tissues remain connected around it. Complex organisms become possible because separate systems can share the same body without every crossing becoming a collision. The difference can be seen in something as ordinary as a knot. A line confined to a plane cannot form a true knot without crossing itself, and any crossing within the plane requires the strands to occupy the same place. In 3 dimensions, one part of a rope can pass over another, then under another, allowing a stable knot to form. The rope has room to weave around itself. Shoelaces, fishing nets, woven cloth, and tangled headphone cables all depend on this freedom, although the last example often seems to use more dimensions than physics officially allows. Linking and knotting are not small decorative details. They show that the 3rd dimension creates structures that cannot exist in a strictly flat world. Containers become possible in a stronger sense as well. A closed surface can isolate an interior volume from the surrounding space. A bottle can hold liquid. A cell membrane can surround the chemical processes of life. A skull can protect a brain. A sealed box can hide an object from every ordinary direction of view. The surface does not need to be infinitely thick. It only needs to form a complete boundary around the volume. Anything moving from the inside to the outside must cross that boundary unless an opening is present. This makes inside and outside central features of our world. We spend much of life moving between enclosed volumes. We leave one room and enter another. We place objects inside bags, drawers, cupboards, and increasingly mysterious storage containers whose contents become unknown within a week. Our bodies themselves are enclosed structures, with skin separating internal tissues from the environment. The 3rd dimension gives objects room to contain other objects, and gives boundaries the ability to hide what lies beyond them. Yet those boundaries are complete only from our own dimensional viewpoint. We can enter a drawn circle without crossing its line by approaching from above the paper. A being with access to a fourth spatial direction could, in principle, enter a sealed three-dimensional room without passing through its walls, floor, or ceiling. It could remove an object from a closed box without opening the lid. It might reach into the center of a solid object without cutting the surface. To us, such actions would appear impossible because every route we know lies within three-dimensional space. This relationship is easier to understand when we remember our position relative to a flat world. A two-dimensional creature sees the boundary of a closed shape and concludes that the interior is inaccessible. We see the entire enclosure from outside its plane. Nothing inside is hidden from our direction of observation. In the same way, a higher dimensional observer might see the complete interior of a three-dimensional body at once. Our skin, bones, and outer surfaces would not block the view, because the observer would not be looking through them along an ordinary direction. From one perspective, this sounds like extraordinary vision. From another, it is simply geometry. We can inspect every point inside a drawn square because the square has no thickness, and we look from a direction outside its plane. A higher observer could relate to our volumes in the same way. A locked safe would not be sealed. A maze would not be confusing. The hidden side of an object would not remain hidden, and the distinction between interior and exterior might look as limited as the distinction between the inside and outside of a circle looks to us when the circle is drawn on a page. Our own vision remains restricted by surfaces. When you look at a cup, you see only the parts facing you. The far side is hidden. The inside may be partly visible depending on the angle, but the material itself blocks light from deeper regions. To understand the whole object, you turn it, move around it, or rely on memory. A three-dimensional object cannot usually be seen completely from one position in ordinary space. This creates the familiar experience of perspective. Nearby objects appear larger than distant ones. One object can hide another. Parallel edges seem to approach one another in the distance. The image formed on the retina is two-dimensional, yet the brain uses shading, motion, focus, and comparison to infodepth. We do not receive the third dimension directly as a complete volume. We reconstruct it from changing flat images and other sensory information. Touch helps confirm what vision suggests. We move a hand around an object, feel its surfaces, and discover its shape over time. The object may be three-dimensional, but our knowledge of it is gathered through a sequence of partial contacts. Even in the space we call home, perception arrives in slices. A shadow gives another example. When a three-dimensional object blocks light, it can cast a two-dimensional projection onto a surface. A sphere may cast a circular shadow. A cube can produce a square, rectangle, or more complicated outline depending on its orientation. The shadow does not reveal the complete object. Different objects can cast similar shadows, and the same object can cast different shadows as it turns. A flat observer seeing only the shadow could attempt to reconstruct the object that produced it. Additional shadows from different directions would provide more information, but the observer might still struggle to determine the complete form. We face a similar problem whenever we try to picture higher dimensional objects. Mathematical diagrams of four-dimensional shapes are usually projections into three dimensions, just as a drawing of a cube is a projection onto a flat page. The picture can preserve some relationships while distorting others. Consider the familiar drawing of a cube made from two squares joined at their corners. No physical cube has edges that pass through one another in the way the flat drawing may suggest. The image compresses three dimensions into two. The brain interprets one square as nearer and the other as farther away. With experience, the representation becomes easy to understand even though it is not a literal cube. A representation of a four-dimensional cube must undergo a similar compression. It may appear as one cube inside another, connected by edges. Those connections represent a direction that cannot be shown directly in our space. The image is not the object itself. It is a lower dimensional projection. useful because it preserves part of the structure. The difficulty is not limited to vision. Our language is built around three-dimensional experience. We describe higher dimensions using words such as beyond, outside, above, and through. But each word already refers to familiar directions. A new spatial direction would not be above the ceiling, beyond the stars, or hidden behind a wall. Those places still belong to the three dimensions we know. The added direction would be independent of all of them. A being able to move through that direction could leave our space without travelling to a distant location within it. From our viewpoint, the being might disappear. From its own viewpoint, it would simply step away. When a flat creature is lifted from its plane, it does not travel toward a faraway point in the plane. It exits the set of positions that the plane contains. A four-dimensional movement would relate to our space in the same way. Three-dimensional space also permits rotation in several ways. An object can turn around different axes, exposing different surfaces while preserving its shape. A flat object can rotate within its plane, but it cannot be flipped over without leaving the plane. We can lift a drawing, turn it through the third dimension, and place it back as a mirror image. This tells us that handedness depends on dimensional freedom. Your left hand and right hand have mirrored structures. No ordinary rotation in three-dimensional space can make one exactly match the other without reflection. A four-dimensional rotation could theoretically turn a three-dimensional object into its mirror image, just as our three-dimensional rotation can reverse a flat figure. A higher dimensional visitor might take a left-handed glove, move it through an extra direction, and return it as a right-handed glove without cutting or rebuilding it. For a living creature, such a transformation would be more serious. Every asymmetric internal structure would be reversed. The heart would change sides. Molecules with handed forms could be mirrored. The result might look normal from the outside while interacting differently with the chemistry of our world. The example is speculative, but the geometry is useful because it shows how a transformation forbidden within one space may become possible in the next. The third dimension also allows objects to avoid one another in ways that flat creatures cannot. Roads can cross using bridges and tunnels. Wires can pass over and under each other. Aeroplanes can travel above cities while vehicles move below. Shelves allow several objects to occupy the same horizontal location at different heights. A building can place many rooms above the same patch of ground. Stacking is one of the most practical gifts of depth. A flat civilization would need to spread every structure across its plane. We can build upward. Cities use towers, basements, tunnels, and layered transport systems, because space in the third direction can be divided and occupied. A small area of ground can contain many floors, each holding people, furniture, pipes, wires, and several cups whose owners no longer remember making them. This freedom supports complexity, but it does not remove limits. We still cannot place two solid objects in exactly the same region at the same time without changing them. We cannot pass through a wall by choosing an unfamiliar angle. We cannot see inside a sealed container without using radiation, sound, cutting, or some other physical process that interacts with the boundary. Our three dimensions provide more routes than a plane, but every route remains inside the same space. The shape of that space is not necessarily as simple as everyday experience suggests. Nearby, ordinary geometry works extremely well. Rooms can be measured using straight lines. Builders can create right angles. Maps can represent local regions with manageable distortion. Across much larger scales, gravity affects the geometry of space-time, and the paths that objects and light follow may differ from the straight paths expected in a perfectly flat setting. It is important here to distinguish three-dimensional space from the four-dimensional space-time used in relativity. Space describes location in three independent spatial directions. Space-time combines those locations with time, allowing events to be described by both where and when they occur. Gravity and general relativity is associated with the geometry of space-time rather than with space alone. Before reaching time, it helps to notice how strongly our concept of an object depends on three-dimensional space. A chair is understood as a solid form with surfaces and volume. A person is understood as a body occupying a region. A planet is a sphere with an interior. Movement means changing spatial position while the object remains recognizably itself. These assumptions work well in ordinary life. A cup does not become a different cup simply because it is moved across a table. A person can travel from one room to another while keeping the same identity. The object changes location, not existence. Time is present during the movement, but we usually treat it as a background measure rather than as part of the object's shape. This familiar view begins to change when we consider that no object remains exactly the same from one moment to the next. A body breathes, cells change, molecules move, and memories form. A wooden table expands slightly with temperature and slowly wears with use. A mountain erodes. A planet moves through its orbit and changes internally. The three-dimensional object observed now is only its current state. We often imagine the object as a stable thing passing through time, rather like a train moving along a track. Relativity encourages a different description. Instead of treating the present object as the whole thing, we can represent its entire history as an extended structure in space-time. The object at one moment becomes a temporal cross-section of something larger. A human body provides a clear example. The body of an infant, the body of an adult, and the body of an elderly person differ greatly, yet they belong to one life. In ordinary experience, these forms appear in sequence. You cannot place your childhood body beside your present body and inspect both as existing moments. You remember the earlier state and anticipate later ones. A viewpoint that could see the full temporal extent would not see a body as a single volume moving through an invisible flow. It would see a continuous history extending from birth to death, changing in shape along the time direction. Every heartbeat, movement, injury, meal, journey, and quiet evening would occupy its own place in that larger structure. From within the life, each moment feels current when it arrives. From a complete space-time description, all those moments belong to the history. This does not automatically settle questions about free will, the openness of the future, or the nature of time. It does show that adding time changes what counts as the complete object. The same pattern appeared at every earlier step. A point became part of a line became an edge or section within a plane became a surface or slice of a solid object. Now the three-dimensional body may become a slice of a four-dimensional history. A two-dimensional resident observing a sphere sees one circle at a time as the sphere passes through the plane. The changing circles are not separate objects. They are sections of one sphere. In a similar way, the body you experience now may be understood as one three-dimensional section of your complete existence through time. The comparison has limits because time does not behave exactly like an ordinary spatial direction. We can move left or right by choice, but we do not move into yesterday in the same way. Time has a directional structure connected with causality, memory, and physical change. Relativity joins space and time while preserving important differences between them. Even so, the dimensional approach helps explain why motion is relative. In ordinary language, an object has a position that changes with time. In space-time, motion becomes part of the object's history. A person standing still and a person walking trace different paths through space-time. Neither one stops moving through the larger structure simply because spatial motion has paused. This reveals an important limitation of the space we call home. 3 dimensions are enough to describe where an object is, but they cannot completely describe an event. Saying that something happened in a room is incomplete without saying when. The same location contains different events at different times. A chair may occupy one corner in the morning and another in the evening. A room may be empty now and crowded later. The place remains while its history changes. Every ordinary experience therefore carries a hidden fourth coordinate. A meeting, a sound, a falling cup, and a spoken sentence occur at both a place and a time. Two people can occupy the same room without meeting if they arrive on different days. Two events can happen at the same moment while being separated by great distances. Space alone cannot organize these relationships. Our bodies also reveal this connection. You do not exist only at one spatial position. You follow a continuous route through locations and moments. Even while lying still, Earth rotates, travels around the Sun, and moves with the solar system through the galaxy. The idea of being stationary applies only relative to a chosen reference. The room around you feels stable because you and the nearby objects share much of the same motion. The bed, walls, and floor move with Earth, so their relative positions change very little. At larger scales, the entire setting is travelling. Three-dimensional space gives the locations, while time is needed to describe how those locations evolve. This is why the third dimension feels complete without being a complete description of reality. It provides the volume in which bodies, rooms, planets, and machines exist. It allows complex life, internal organs, containers, knots, layered cities, and movement around flat barriers. It gives us the world of solids and surfaces, the world our senses are built to navigate. It also hides its own limitations, and we see only surfaces from one viewpoint. We experience objects one moment at a time. We cannot look directly into sealed interiors or leave space through a higher direction. We treat the present form of an object as complete even though it belongs to a history extending beyond the moment. The next step will not simply add another direction beside left, right, forward, backward, up and down. It will connect location with time and replace the idea of a changing object with the larger history of that object. A person will no longer be only a body occupying space. A journey will no longer be only movement between places. Every event will take its position within space-time, and the familiar present will become one part of a structure that different observers may divide in different ways. Three-dimensional space tells us where something is, but it cannot tell us when it is there. A room may contain a chair in the morning, a group of people in the afternoon, and nothing but a forgotten cup by night. The location has not changed, yet the events occupying it are different. To describe any event completely, we need more than left and right, forward and backward, and up and down. We also need a position in time. This is why modern physics combines the three dimensions of space with time into a single structure called spacetime. An event is not merely something that happens somewhere. It happens somewhere at a particular moment, and changing either the place or the time gives us a different event. Calling time the fourth dimension can create a misleading picture. It may sound as though time is simply another spatial direction, like a hidden route beside the familiar three, and that with the correct turn we might walk into yesterday as easily as we walk into another room. Physics does not treat time as identical to space. Space and time are connected, but they behave differently. You can choose to move left or right, climb upward or descend and return to a place you visited earlier. You cannot freely reverse your movement through time. You remember the past rather than the future. Causes normally come before their effects, and every ordinary object proceeds from earlier moments toward later ones. Time belongs to the dimensional description of reality, but it carries a different role from the spatial directions. The connection becomes clearer when we think about a moving object. Imagine a person walking through a room. At the beginning, the person stands near the door. A few moments later, the person is beside the table. Later still, the person reaches the window. A three-dimensional description gives the person's position at each moment, but those separate descriptions can be joined into one history through space-time. Instead of imagining a body that vanishes from one place and appears in another at each new instant, we can describe a continuous path containing every position the person occupies throughout the walk. Physicists often call this path a world line. The word line can be slightly deceptive because a human being is not a point, and a complete body extended through time would form a much larger structure. Still, if we simplify the person to a single location, the sequence of positions traces a line through space-time, A person sitting still traces one kind of world line, a person walking traces another, a spacecraft travelling at great speed traces another. Every object follows its own route through the combined structure of space and time. This means that even when you are not moving across the room, you're not stationary in space-time. Moments continue to pass. Your spatial location may remain nearly unchanged relative to the bed or chair, but your position in time does not remain fixed. The version of you listening now is not located at the same event as the version who heard the previous sentence. The difference may be small, yet the two moments occupy distinct places in your history. From ordinary experience, these moments arrive one after another. You never encounter your entire life at once. You experience the current state of your body, remember some earlier states, and imagine possible later ones. Physics can represent the full history differently. Your life may be described as an extended structure with a beginning, a changing shape, and an end point. The infant you once were, the person listening now, and the older person you may become are not separate individuals in this description. They are different temporal sections of one continuous existence. The comparison with a three-dimensional object passing through a flat world is useful here. A flat observer sees one cross-section of a sphere at a time. The visible circle appears, changes size, and disappears. The observer may treat each changing circle as the current form of the object. From our viewpoint, every circle belongs to one complete sphere. In a similar way, the body you experience at this moment can be treated as one three-dimensional section of your life extended through time. The complete structure would not look like an ordinary human body. Its shape would include every movement and physical change across a lifetime. Where you remained still, nearby moments would occupy similar spatial locations. Where you travelled, the structure would stretch across space as time advanced. A journey to another country would become a long connection between the places involved. The motion of your hands, the beating of your heart, and the changing arrangement of every part of your body would contribute to an extraordinarily complicated history. If a being could somehow view this complete structure from outside our ordinary experience of time, it would not see you as a single body located in the present. It would see your entire life. Your first breath and your final moment would be separated within the structure in much the same way that your head and feet are separated within your body. Events you remember as distant would occupy different temporal locations, but all would belong to the same complete history. Such a viewpoint would transform the meaning of movement. We normally say that a person moves because the person's position changes over time. In the complete space-time picture, the motion is already part of the shape. A winding world line represents a changing position. A straighter one represents less spatial movement. The person does not need to slide through the completed history for the history to exist as a geometric object. The entire route can be described as one structure. This is often connected with the idea of a block universe, in which past, present, and future are all parts of space-time, rather than the present being the only real moment. The block universe is a philosophical interpretation inspired by relativity, not a simple experimental statement that resolves every question about time. It is useful because relativity does not provide one universal present shared by all observers. Different observers can divide space-time into space and time in different ways, especially when they move relative to one another. In everyday life, we assume that distant events happen at the same time if clocks show matching readings. This works well when speeds are low and distances are modest. Relativity reveals that simultaneity is not absolute. Two events that one observer regards as happening at the same time may be assigned different times by another observer moving relative to the first. Imagine two flashes of light occurring at opposite ends of a moving train. An observer standing beside the track may judge the flashes to be simultaneous if the light from both reaches the observer in a suitable way. A passenger moving with the train may judge one flash to have occurred before the other, because the passenger moves toward one signal and away from the other. Careful treatment accounts for the travel time of the light, yet the disagreement about simultaneity remains. It is not caused by faulty clocks or slow human reactions. It comes from the structure of spacetime. This result removes the idea of a single cosmic now extending across the entire universe. There is no universally agreed surface separating all past events from all future events for every observer. Nearby people moving slowly relative to one another will agree closely enough for daily life, which is fortunate because arranging meetings would otherwise become even more difficult. At high speeds and large distances, the differences become significant. The speed of light plays a central role. Every observer measuring light in a vacuum obtains the same speed, regardless of the observer's own motion. This seems impossible from the viewpoint of ordinary motion. If someone throws a ball from a moving vehicle, a person beside the road combines the speed of the vehicle with the speed of the throw. Light does not behave in that simple way. Preserving the same measured speed for all observers requires space and time to adjust together. One consequence is time dilation. A moving clock can record less elapsed time between two events than a clock following a different path through space-time. This does not mean that the moving clock becomes defective. Every process travelling with it changes consistently. A person's heartbeat, thoughts, chemical reactions and aging all follow the same elapsed time measured along that person's path. The effect is extremely small at ordinary speeds, which is why you do not return from a bus journey noticeably younger than the people who stayed at home. At speeds approaching that of a light, the difference becomes large. A traveller could make a high-speed journey and return having experienced much less time than people on Earth. Both the traveller and the people who remained behind would feel their own clocks running normally. The difference would appear when their histories met again, and the elapsed times were compared. This idea is often illustrated with twins. One travels through space at very high speed while the other remains on Earth. When the traveller returns, less time has passed for the traveller, who is therefore younger. This is not an illusion caused by delayed signals. It is a genuine difference in the amount of time measured along the two pairs through space-time. The situation is sometimes called a paradox because each twin might initially seem entitled to say that the other one was moving. The journeys are not completely symmetrical, however. The travelling twin changes direction in order to return and follows a different path through space-time. The amount of elapsed time depends on the complete route, and the routes are not equivalent. Time dilation has been measured with precise clocks carried on aircraft and satellites. Particles moving at high speed also survive longer from the viewpoint of a laboratory than they would if they were at rest. These observations confirm that time is not a universal background ticking identically for every object. The amount of time between events depends on the path taken through space-time. Gravity changes time as well. General relativity describes gravity through the geometry of space-time. Matter and energy affect that geometry, and objects follow paths within it. The stronger the gravitational field, the more slowly a clock runs compared with a clock located where gravity is weaker. A clock nearer Earth's surface runs slightly more slowly than a clock at a greater altitude. The difference is tiny, but modern clocks can measure it. Your feet are technically aging at a slightly different rate from your head because they are closer to Earth's centre, although this is not a useful explanation for tired legs. Near a very massive object, the effect can become much stronger. A clock close to a black hole would run more slowly relative to a distant clock. To an observer far away, processes near the black hole may appear increasingly slowed as the object approaches the boundary known as the event horizon. The falling observer experiences local time normally and may cross that boundary without noticing a sudden physical wall, assuming the black hole is large enough that other destructive effects are not immediately overwhelming. Gravity and motion therefore influence the shape and duration of a life. Two people can begin together, follow different routes through the universe, and reunite having aged by different amounts. Their bodies are not travelling through one universal time at different apparent rates. Each follows a path with its own measured duration. This has practical consequences. Navigation satellites move rapidly relative to Earth's surface, which affects their clocks through motion. They are also farther from Earth's gravity, which affects their clocks in the opposite direction. The systems must account for both effects. Without those corrections, Positioning errors would grow, and navigation would quickly become unreliable. The map on a phone works partly because engineers treat time according to relativity, rather than assuming that every clock in the universe agrees automatically. Spacetime also limits which events can influence one another. Light and other causal signals travel at finite speeds. An event can affect only regions reachable by signals moving no faster than light. Events too far apart in space and too close together in time cannot have a direct causal connection. This creates a structure around every event. Some events lie in its causal past and could have influenced it. Others lie in its causal future and may be influenced by it. A third group is separated in such a way that no signal travelling within the known limit could connect them at those times. Different observers may disagree about the time order of these causally disconnected events, but they agree on the order of events linked by cause and effect. This protects causality within relativity. If one event causes another, observers do not simply reverse that relationship by changing their motion. The flexible ordering of distant events does not turn effects into causes. Space-time allows disagreement about simultaneity, while preserving the connected chains through which physical influence travels. For human life, these limits define what can be known and affected. Light from a distant star may have travelled for years before reaching your eyes. You see the star as it was when the light began its journey, not as it exists at the moment you receive the signal. Looking into space is also looking into the past. The moon appears as it was a little more than a second earlier. The sun appears as it was several minutes earlier. Distant galaxies appear as they were millions or billions of years ago. No observer receives an instantaneous picture of the universe. Every view is assembled from signals arriving from different distances and different earlier times. This means the night sky is not a single present scene. It is a collection of histories. Nearby objects are shown relatively recently. Distant ones are shown much earlier. A telescope does not merely bring faraway places closer. It allows us to observe older sections of the universe's development. The same delay exists on smaller scales, although it is too brief to notice. When you look across a room, light takes time to reach you. The person you see is always the person from a tiny fraction of a second earlier. Daily life feels immediate because the delays are extremely small, and the brain processes information efficiently. But direct access to an exact universal present is not available even in principle. Your personal present is therefore a local experience shaped by signals, memory, and the operation of the brain. Physics describes events and their relations without identifying one moving present that all of reality shares. This does not make the present unreal as an experience. It means that the experience of now is not a universal dividing line built into space-time in the simple way people once assumed. Memory adds another layer. You carry records of earlier events through changes in the brain, photographs, objects, and written information. You do not carry records of future events. This difference contributes to the direction in which time is experienced. Physical processes create traces as events occur, allowing the past to influence the present. The direction of time is closely related to increasing entropy, the tendency of closed systems to move toward more probable and less ordered arrangements. A cup may fall and break into many pieces, but the pieces do not normally gather themselves and leap back onto the table. Heat spreads from warmer objects to cooler surroundings rather than spontaneously concentrating itself. These processes create a practical distinction between earlier and later states. The fundamental equations describing many physical processes can work in either time direction, yet large systems overwhelmingly develop toward higher entropy. This gives ordinary experience its arrow. We remember unbroken cups and observe broken pieces afterward. We prepare food and then digest it. We grow older rather than returning to childhood. The sequence is not merely a habit of language. It reflects the statistical behavior of enormous numbers of particles. A complete space-time description does not erase this arrow. The history of a life still contains an ordered pattern of development. Memories occur after the events they record. Biological aging proceeds in one direction. Causes leave effects. Even if the entire history is represented as one structure, the internal relationships within that structure are not random. This distinction helps avoid a common misunderstanding. Seeing a life as a complete shape does not mean every moment feels equally accessible to the person living it. A road can exist as a whole on a map, while a traveller occupies only one part of it. The traveller cannot reach a distant section without following a route. In the same way, a spacetime model can include an entire history, while the observer within that history experiences events in sequence. The road comparison is imperfect because time is not simply another stretch of ground, but it shows how a complete structure and a local experience can coexist. The map does not force the traveller to feel every location at once. The space-time description does not force a person to experience every age simultaneously. It does raise difficult questions about choice. If the future is part of a complete space-time structure, are decisions already fixed? Some philosophers argue that the block universe is compatible with meaningful choice because decisions are part of the structure rather than events imposed from outside it. You choose according to your reasons, desires, knowledge and character, and those processes belong to the history. Others believe that the future should be treated as genuinely open, or that quantum uncertainty prevents one fixed account of all later events. Physics does not provide a universally accepted answer to every philosophical question about free will. Relativity changes the structure of time, but the interpretation of human choice requires additional assumptions. Quantum mechanics introduces probabilities that cannot always be understood as simple ignorance about a predetermined outcome. Depending on the interpretation, the future may involve genuine alternatives, hidden variables, branching histories, or other structures. This is where the dimensional staircase begins to move away from strict spacetime geometry and toward broader conceptual models. Before taking that step, it is worth returning to the shape of one life. Imagine every place you have visited connected through time. Your home, school, workplaces, journeys, and quiet moments form parts of one continuous history. Encounters with other people occur where your histories intersect. Two lives may remain close for years, separate across great distances, and meet again later. A conversation is a region where two human histories exchange sound, light, and information. A friendship becomes a repeated pattern of intersections and shared paths. A family is not only a group of bodies existing now, it is a network of connected histories extending through time. A photograph captures light from one brief section of that network. It freezes a three-dimensional arrangement into a two-dimensional record. The people in the image continue through time, but the photograph preserves evidence of one earlier configuration. Looking at an old picture feels unusual because your present mind compares two distant sections of the same lives. The child in the image may no longer exist as a current body, yet that child has not become unrelated to the adult looking at the photograph. Both belong to the same continuous history. The shape has changed, but the connection remains. Identity becomes less like a fixed object and more like continuity through change. The atoms in your body are replaced, your appearance develops, and your memories accumulate. There may be no single unchanging piece of matter that remains identical throughout your life. What persists is the organized connection between states. Space-time makes that continuity visible in the model. You are not only the body at the present moment, you are the connected history that led to it and continues from it. The current body is where awareness is operating now, but it belongs to a larger physical process. From a hypothetical viewpoint with access to the whole structure, birth and death would appear as boundaries of the life rather than as moments approaching or receding. Childhood would occupy one region, adulthood would occupy another. Journeys, relationships, illnesses, recoveries, and ordinary evenings would all have positions. Such a being might know your future in the same way that you can see the far end of a road from above. Whether this kind of observer is physically possible is another question. Relativity lets us describe the structure mathematically, but it does not give us a practical place outside space-time from which to inspect the universe. There may be no external time in which a viewer could wait while looking at our complete timeline. Any real observer would normally belong to space-time and possess a history of its own. The idea of standing outside time is useful for imagination, but difficult to define physically. Outside and before are concepts drawn from the very structure we're trying to leave. This is one reason higher dimensional discussions become more speculative after space-time. The first 3 dimensions describe familiar spatial directions. Time belongs to tested physical theory, though it behaves differently from space. Moving beyond space-time into alternative histories requires assumptions about what counts as another direction or another level of reality. A possible next step is to treat the complete history of our universe as one path among other histories that could have unfolded. In one history, a person chooses one route. In another, the person chooses differently. In one, an event occurs. In another, a different outcome appears. Instead of seeing one life extended through time, a higher viewpoint would contain many possible versions of that life. This would change identity again. The person would no longer be represented only by the history actually experienced. The larger structure might include every allowed path emerging from earlier conditions. A decision would become a branching region rather than a single turn. The shape of a life would expand into a collection of possible lives. Physics does not establish this simple dimensional ladder as a literal map. Alternative timelines arise in some interpretations of quantum mechanics and in many speculative models, but describing them as a 5th dimension is a conceptual choice. It is useful because it repeats the pattern we have followed. A lower observer experiences one section or path, while a higher viewpoint contains the broader set. The 4th dimension gives a body a history. The next level will ask what happens when one history is no longer the complete object. Instead of following only the path that occurred, we will consider the wider space of paths that might have occurred, where different decisions, accidents, and quantum outcomes create neighbouring versions of reality that no ordinary traveller can reach by moving through space or waiting through time. Once a life is understood as a complete path through space-time, the next question is whether that path is the only one that could exist. You experienced one sequence of events. You woke on particular mornings, met certain people, made specific decisions, and arrived at this moment through a route that now forms your remembered past. Yet many points along that route appear to have contained alternatives. You could have answered a question differently, taken another road, accepted an invitation, refused an offer, left earlier, waited longer, or chosen a breakfast that did not require explaining crumbs to the person responsible for cleaning the sofa. Some alternatives were important, while others would barely have changed the afternoon. From inside one life, those unused possibilities seem to disappear as soon as a choice is made. The path continues in one direction, and the routes not taken remain ideas rather than places we can visit. The 5th dimension in the conceptual ladder we are using treats those unrealized paths as part of a larger structure. This is not a standard scientific definition accepted across physics. Physicists use the word dimension in precise mathematical ways, and theories with additional dimensions usually describe extra coordinates rather than a simple staircase of increasingly large collections of universes. Here, the 5th dimension is a way of organizing possible histories. The 4-dimensional space-time of one universe becomes one complete path, and the next level contains alternative paths that begin from related conditions but develop differently. Imagine your life as a long road drawn across a map. The road contains every event you actually experienced, beginning with your earliest physical development and continuing through the present. At several locations, other roads might have been available. One turns toward a different school, another leads to another city. One contains a friendship that never began in your experienced history. Another avoids an accident that occurred. A third produces an accident that did not occur. From your position on the road, the junction behind you is settled. You remember which way you travelled. From a viewpoint above the entire network, every route could be displayed together. This does not mean every imagined possibility must exist physically. A person can imagine opening a cupboard and finding a fully grown whale inside, but ordinary cupboard dimensions and whale dimensions do not cooperate with that scenario. Possibility is limited by whatever rules govern the system. A branch must develop from an allowed state through an allowed process. Within one fixed set of physical laws, many outcomes may be possible, but not every sentence we can form describes one of them. The fifth dimensional picture therefore begins with histories that share the same broad physical framework. Gravity behaves in the same general way. Matter follows the same underlying rules. The universe begins with the same or closely related conditions, but events develop along different routes. A particle produces one result in one history and another result in a neighbouring history. A storm changes direction. A message arrives earlier. A person pauses at a crossing rather than continuing. Small differences may remain small, or they may grow into completely different futures. Weather provides an ordinary example of how tiny differences can expand. The atmosphere is governed by physical laws, yet predicting its exact state far into the future is difficult, because small uncertainties in present conditions grow over time. A slight change in temperature, pressure, or airflow can eventually alter the path of a storm. This does not prove that every weather outcome exists in a separate universe. It shows how one set of rules can permit many possible developments when the starting information varies or cannot be known perfectly. Human history works in a similarly complicated way. A delayed train may cause two people not to meet. That missed encounter may alter relationships, jobs, families, and future decisions. One small change can spread through a network of causes until the later world looks very different. Looking backward, we often identify famous moments and ask what would have happened if one decision had changed. Those questions are difficult because history is not controlled by one isolated switch. Changing one event affects many others, and the consequences interact. A fifth dimensional observer in this metaphor would not need to guess each alternative separately. It would see the larger branching structure. Our experienced spacetime would be one route within it. The observer might compare histories in which the same early conditions lead to different later events. It could see where paths remain similar, where they separate, and whether any later states become alike again. From our lower viewpoint, an alternative history is inaccessible. Moving left, right, upward or downward will not reach it. Waiting longer will only carry us farther along the history we already occupy. Even travelling backward in time, if that were possible, would not automatically place us on a different branch. It might return us to an earlier part of the same history, or create difficult questions about how changes relate to the original path. To move between branches, a traveller would need a freedom beyond ordinary space-time. The movement would not be a journey across kilometres or years. It would be a change in which complete history the traveller occupies. One moment the traveller belongs to a world where a particular event happened. The next moment, from the traveller's perspective, the surrounding history contains a different outcome. Science fiction often treats this as changing timelines. A character enters a machine, crosses a glowing doorway, or presses a control that was clearly designed without consulting anyone familiar with safe laboratory practice. The character emerges into a world that resembles home but differs in a few important ways. A familiar person has made different choices. A building stands where an empty field once existed. A historical event ended differently. The setting remains recognizable because the branch shares much of its past with the original. The dimensional analogy helps explain why the transition would seem impossible to observers who remain within one history. A flat creature cannot understand how an object leaves a sealed region without crossing its boundary. A three-dimensional person cannot understand how a traveller leaves one complete space-time without passing through its ordinary past or future. In each case, the higher route lies outside the available directions of the lower world. There is a tempting connection here with the many worlds interpretation of quantum mechanics. In that interpretation, quantum processes do not select one outcome by destroying all the others. Instead, the total quantum state develops into branches in which different outcomes are observed. An observer becomes correlated with one result in one branch and another result in another branch. The branches are not normally treated as roads through which people can freely travel. They become effectively separate because interaction between them is suppressed through a process called decoherence. The many worlds interpretation is a serious interpretation of quantum theory, but it is not confirmed as the one correct account of reality. Other interpretations describe measurement differently. Some treat outcomes as genuinely probabilistic. Some add hidden structures. Some focus only on the predictions and avoid claiming a detailed picture of what exists behind them. Experiments strongly support quantum mechanics, but several interpretations reproduce the same observed results, making them difficult to distinguish. The fifth dimensional ladder should therefore not be presented as proof of many worlds. It uses branching histories as a model for a higher level of possibility. The model may resemble ideas found in quantum theory, but resemblance is not confirmation. If all alternative histories existed, identity would become more complicated. The person you call yourself would occupy one branch, but other versions would share part of your past. Up to a certain event, two versions might be physically identical. After that point, their experiences would differ. One remembers accepting an opportunity while the other remembers declining it. Both continue from the same earlier person, and neither has a stronger claim to being the original after the split. From inside each branch, there would be no sensation of dividing. Each version would experience one continuous life. Neither would see the other disappear. The branching would be visible only in the larger description. This resembles the way one road can divide into two while each traveller experiences only the route taken. The map contains both paths, but the person walking experiences one sequence of ground beneath the feet. The number of branches would be unimaginably large if every quantum event and every complex physical interaction contributed to different histories. There would not be only a few dramatic alternatives in which empires rise differently, or famous inventions arrive earlier. Differences would occur at every scale. Particles would scatter in different ways, molecules would move differently, raindrops would land in other places. Most branches would not contain exciting changes suitable for a film. They would differ in details so small that nobody would notice them. Over time, small variations could create larger differences. A microscopic event might influence a nerve signal, which could influence a decision, which could alter a conversation. Whether such amplification occurs in a particular case depends on the physical chain involved. The general point is that the branching structure would be far denser than a simple tree showing a few major life choices. The image of a tree is useful, but it can also mislead. A tree has clear branches that separate at visible points. Quantum histories may not divide into perfectly defined worlds with neat boundaries. The structure is mathematical and depends on patterns of interaction. What counts as a distinct branch may be approximate rather than absolute. The tree helps the human imagination, but reality is under no obligation to arrange itself like a diagram in a school notebook. The sixth dimension in our conceptual ladder broadens the collection. Instead of containing only different histories that unfold under the same general laws, it includes universes that begin with different initial conditions and perhaps different values for the basic features of physics. The universe might contain more matter, less matter, a different distribution of energy, or altered strengths for the interactions that govern particles and forces. This step moves from alternative stories within one kind of universe to alternative kinds of universe. The difference is similar to comparing several games played under the same rules and then comparing games in which the rules themselves have been adjusted. In the fifth dimensional picture, the pieces and rules remain broadly fixed while the moves vary. In the sixth, the board may be arranged differently, the pieces may behave differently, and certain moves may not exist. Consider gravity. In our universe, It allows matter to gather into stars, planets, galaxies, and larger structures. If its effective strength was substantially different while other features remained unchanged, cosmic history could develop in another way. Stronger gravity might cause matter to collapse more rapidly. Weaker gravity might make large structures harder to form. The details are complex because changing one property affects many processes, but the example shows that a universe can differ at a deeper level than one historical decision. The masses and properties of fundamental particles also matter. The stability of atoms, the behavior of stars, and the chemistry needed for complex structures depend on relationships among these properties. A universe with different values might contain unfamiliar atoms, brief stars, or no stable matter of the kind we know. It might possess rich structures that our theories could describe, or it might remain nearly empty and uneventful. The number of large spatial dimensions could differ as well. We have already seen that geometry changes what kinds of movement and structure are possible. A universe with 2 large spatial dimensions would face severe limits on complex bodies. A universe with 4 large spatial dimensions would allow movements and arrangements unavailable to us, but the behavior of gravity and stable orbits might also change. The existence of an extra direction does not guarantee a more elaborate version of ordinary life. It may prevent familiar structures from forming at all. This is where the word universe needs careful handling. In everyday speech, the universe means everything that exists. In cosmology, physicists sometimes discuss a multiverse containing many regions or universes with different conditions. Those proposals arise in several contexts, including cosmic inflation, quantum theory, and speculative high-energy physics. They do not all describe the same thing, and none should be treated as established simply because the word multiverse has become familiar. Some models of cosmic inflation suggest that the rapid expansion associated with the early universe may continue in distant regions, producing separate cosmic domains. Each domain could develop as an observable universe of its own. Depending on the underlying physics, conditions might vary among them. These domains would not necessarily sit beside one another like bubbles floating in ordinary space. The geometry of the larger process can be more complicated, and the regions may remain permanently out of causal contact. Other proposals arise from theories containing many possible stable arrangements of fields and extra dimensions. Different arrangements could produce different effective physical laws at lower energies. In one region, particles might have certain properties. In another, the values could differ. The full theory would remain the same at a deeper level, while its local expression would vary. These ideas are active areas of theoretical discussion, but direct evidence is limited. If other universes cannot exchange signals with ours, testing their existence becomes extremely difficult. A proposal may still have scientific value if it follows from a broader theory that makes testable predictions here, but simply adding invisible universes to explain anything would not be enough. A good theory must remain constrained by observation. In our dimensional metaphor, a 6th dimensional observer could survey universes with different starting conditions and physical settings. It might see one universe filled with long-lived stars, another dominated by black holes, another expanding too rapidly for galaxies to form, and another containing forms of matter we would not recognize. Our entire cosmic history would become one case in a broader library. The library comparison is useful. The 5th dimension resembles many editions of one story, beginning similarly but developing through different events. The 6th resembles a collection written with different settings, characters, and rules. Some books contain familiar worlds with altered histories. Others describe realities where the basic ingredients are different. A reader outside the collection can compare them, while a character inside one book experiences only the rules printed on its pages. The character may attempt to discover those rules through experiments. It drops objects, observes light, studies matter, and develops equations describing regularities. From within the story, those regularities appear fundamental. The character cannot tell, simply by local observation, whether the rules are the only logically possible ones or one selection from a larger collection. We're in that position. Physics identifies the laws and constants that describe our observable universe, but a deeper question remains. Why these laws and values rather than others? Some may be forced by a more fundamental theory. Some may arise from the history of the early universe. Some may vary among regions in a larger reality. Some may be the only combinations capable of supporting observers who can ask the question. This last idea is connected with anthropic reasoning. Any observer naturally finds itself in conditions compatible with the existence of observers. A universe that cannot form stable structures, complex chemistry, or long-lasting sources of energy will not contain beings wondering why the environment supports them. If many universes with different properties exist, our observations may be influenced by this selection effect. Anthropic reasoning can be useful, but it must be handled carefully. It does not explain every feature by saying that we are here. It identifies a constraint on what observers can expect to measure. To become scientifically powerful, it needs a well-defined set of possible universes and some account of how those possibilities are distributed. Without that, almost any observed value might be declared unsurprising after the fact. The sixth-dimensional picture also affects individuality. In the fifth dimension, alternative versions of you share the same basic biology and physical laws. In the sixth, many universes may not contain humans at all. Some may not contain atoms. Some may not contain stars. Others might support complex systems that bear no resemblance to terrestrial life. A higher observer looking across this collection would not treat humanity as a central feature of reality. We would be one local arrangement permitted by one set of conditions. The human body, which seemed complete in 3 dimensions and became a temporal structure in 4, now becomes a special outcome within a much wider range of possible structures. This does not reduce the value of a human life. Importance and frequency are different ideas. A rare arrangement is not meaningless because it is rare. The broader view simply removes the assumption that reality must be organized around forms familiar to us. The 7th dimension takes the conceptual expansion still farther. It does not contain merely different histories or different physical constants within a shared deeper framework. It represents every universe allowed by every logically consistent set of laws. The rules governing space, time, matter, causality, and information could differ. Some realities might contain dimensions unlike ours. Some might lack time in any familiar sense. Some might consist entirely of mathematical relations without particles or fields resembling those in our theories. At this level, the word universe becomes almost too narrow, because the collection includes realities with no shared background. 2 universes may not differ like 2 countries or even 2 games. They may have no common definition of distance, object, event, or change. One may contain a continuous space. Another may be a discrete network. One may have a single time direction. Another may have several temporal structures or none at all. A comparison between them would require very general language. Logical consistency becomes the proposed boundary. A reality cannot contain a statement and its direct contradiction in the same sense at the same time without making meaningful description collapse. Beyond that restriction, the range may be enormous. Any coherent mathematical structure might be treated as a possible world. This resembles the idea sometimes called a mathematical universe, in which physical existence and mathematical consistency are deeply connected. According to the strongest version, every mathematical structure exists in the same broad sense, and our universe is one structure experienced from within by observers that arise inside it. This is a philosophical and speculative proposal, not an established result of physics. The appeal is easy to understand. Mathematics describes nature with remarkable success. If our universe is one mathematical structure, perhaps other structures are equally real. The difficulty is equally clear. It is hard to define what physical existence adds, how probabilities should be assigned across every structure, and how a proposal containing all possibilities can make distinctive predictions. A theory that allows everything risks explaining nothing unless it also explains why an observer should expect one experience rather than another. If every consistent universe exists, why do we find ourselves in this one? The answer cannot simply be that this one permits us, because many possible universes might permit observers. We would still need a way to compare them. The seventh dimensional metaphor therefore reaches the border between physics, mathematics, and philosophy. The earlier dimensions could be understood through movement and geometry. The fifth and sixth involved speculative extensions of histories and laws. The seventh asks what it means for any coherent reality to exist at all. A seventh dimensional observer is almost impossible to describe without contradiction, because an observer normally belongs to some structure. It has states, receives information, and experiences relations. To stand outside every possible logical structure would require the observer not to belong to any of them, which leaves no framework in which it could think or act. The observer is therefore best treated as a perspective in the explanation, rather than as a literal creature waiting above the multiverse. From that imagined perspective, our universe would be one complete object among an unrestricted collection. Its entire space-time, every galaxy, every life, and every event would be contained within one structure. Nothing happening inside it would surprise the higher view, because the whole arrangement would be available at once. Alongside it would be realities sharing some of its features, and others sharing almost none. The distinction between possible and actual would then become difficult. We normally call our history actual and unused alternatives possible. In a branching model where every outcome occurs, each branch is actual to its own inhabitants. In a multiverse containing different laws, each universe is real from within. If every logically consistent structure exists, actuality may become a local word meaning the reality occupied by the speaker. The word I would also become local. In 3 dimensions, you identify with a present body. In 4, you can be described as an entire life. In 5, there may be many continuations sharing your earlier history. In 6, there are worlds where related forms arise under different conditions and many worlds where nothing like you appears. In 7, identity is one pattern among every coherent pattern capable of existing. At that scale, movement loses its familiar meaning. A move across space changes location. A move through time changes the moment experienced. A hypothetical move through the 5th dimension changes history. A move through the 6th changes the physical setting. A move through the 7th would change the entire logical framework that defines movement, traveller, and destination. It is not clear that anything could survive such a transition, because the conditions supporting the thing might not exist on the other side. A person transported into a universe with different chemistry might immediately cease to function. In a reality with different dimensions, the arrangement of the body could become impossible. In one without time, there may be no process of arrival. In one without persistent objects, there may be no identity to preserve. Travel assumes enough continuity between origin and destination for the traveller to remain recognizable. At the 7th level, that continuity is not guaranteed. This reveals a limit hidden within most stories about parallel universes. The traveller usually arrives with body, memory, and equipment intact, because the destination follows laws similar enough to support them. Truly different laws might not allow the traveller's atoms, signals, or thoughts to exist. The doorway would not merely lead to an unusual landscape, it could lead to a reality in which the idea of a doorway has no meaning. The dimensional staircase has now moved far from the simple geometric point where it began. 0 dimensions gave us location without movement. 1 dimension provided a line and 2 directions. 2 dimensions allowed paths to turn and boundaries to enclose areas. 3 dimensions created volume, internal structure, and the space of ordinary bodies. 4 dimensions joined each body to its history. 5 dimensions expanded one history into alternative histories. 6 dimensions broadened one set of laws into different possible physical universes. 7 dimensions extended the collection toward every logically consistent reality. Each step made the lower object part of a larger structure. A point became part of a line became part of a plane became part of a volume, a body became part of a space-time history, a history became part of a branching collection, a universe became part of a collection of universes, and that collection became part of the widest possible field of coherent existence. The pattern suggests that no observer inside a level can easily confirm the full structure above it. A flat scientist can measure cross-sections of a passing sphere but cannot see the whole sphere directly. We can measure our universe and develop theories about its larger context, but evidence becomes harder to obtain as the proposed level moves farther beyond causal contact. This is why careful language matters. Branching timelines are not simply the 5th dimension, according to all physicists. Changing physical laws are not universally defined as the 6th. Every logical universe is not an experimentally confirmed 7th dimension. These are conceptual stages designed to extend the lower dimensional analogy. Their value lies in showing how a complete reality at one level might become only one member of a wider set at the next. Used carefully, the framework reveals how dependent our ordinary concepts are on position. The present feels unique because we experience one moment. Our history feels unique because memory follows one path. Our laws feel necessary because every experiment available to us occurs under them. Our universe feels complete because its observable contents define the largest physical system we can investigate directly. A higher collection would change those judgments without making our local experience false. The present would remain the moment you experience. Your history would remain the path you remember. Physical laws would still govern every process around you. The universe would still contain everything that can affect us directly. The broader perspective would show that local completeness is not the same as absolute completeness. Even this 7th level may not mark a final boundary. Once every possible universe is included, the mind can still ask whether there are different sizes of infinity, whether all possibilities can be gathered into one complete collection, and whether the word every hides problems that ordinary language cannot resolve. The staircase does not end merely because the available descriptions have become difficult. It continues toward the idea of infinity, where adding one more possibility may change nothing, where a set can contain endless worlds without becoming the largest set imaginable, and where the attempt to include everything leads us to the edge of what mathematics and language can consistently hold. After expanding from one universe to every logically consistent kind of universe, it is tempting to think that the journey must finally be complete. If every possible history, every possible law of physics, and every possible form of reality has already been included, there seems to be nowhere left to go. Yet the word every hides a difficult question. Can all possibilities truly be gathered into one complete collection, or does the idea of totality change when infinity enters the discussion? This is where the dimensional staircase stops behaving like an ordinary staircase. Earlier steps added one new freedom at a time. A point gained length, a line gained width, a plane gained depth, and a body gained a history. The later levels added possible histories and possible universes. Infinity is different. It is not simply another direction waiting beside the others. It is a property of collections, distances, processes, and structures that do not come to an end, and it can appear in more than one form. People often use infinity as though it were an extremely large number. We may say that something will take forever, that there are infinitely many tasks waiting on a desk, or that a queue extends to infinity when it merely reaches the door and contains one person who has forgotten what they intended to order. In mathematics, infinity is more precise. It does not describe a number that is merely larger than all the numbers we have happened to count so far. No matter how large a finite number becomes, another can always be produced by adding one. Infinity describes the fact that this process has no final stopping point. There is no largest ordinary whole number waiting at the end of counting, with a small sign beside it saying that the system is now complete. This means infinity cannot be reached by counting for a very long time. A person could count for years, a computer could continue for longer, and a machine operating until the stars faded could still have reached only a finite number of steps. Every completed stage would have a next stage available. Infinity is not the final item in the sequence. It describes the absence of a final item. This difference sounds minor, but it prevents many common mistakes. Treating infinity as a very large ordinary number leads to questions such as what happens when one is added to it, whether two infinities can be compared, and whether removing part of an infinite collection makes it smaller. The answers do not behave as they would for finite quantities. Imagine a hotel with a finite number of rooms. If every room is occupied, a new guest cannot be accepted unless someone leaves or agrees to share, which tends to reduce the calm atmosphere expected of a respectable hotel. Now imagine a hotel with endlessly many rooms, one room for every positive whole number. Every room is occupied, yet one more guest arrives. The manager can move the guest in the first room to the second, the guest in the second to the third, and continue in the same pattern. Every existing guest receives a room, and the first room becomes available for the newcomer. The hotel was full, but it still had room. This example is known because it shows how infinite collections differ from finite ones. In an ordinary hotel, moving every guest one room forward fails when the final guest reaches the end and finds no next room. The infinite hotel has no final room. Every guest can move and no one is pushed outside the building. The result feels like a trick because our common sense developed around finite objects. A basket containing 10 apples cannot accept an 11th without changing the count. An infinite collection can be paired with a proper part of itself and still contain the same number of members in the mathematical sense. Consider all positive whole numbers. Now consider only the even ones. The even numbers seem like half of the whole numbers because every second number is missing, yet each positive whole number can be paired with exactly one even number by doubling it. The first whole number pairs with the second even position, the second whole number pairs with the next, and the pairing continues without leaving anything out. The set of even numbers is contained inside the set of whole numbers, but both have the same infinite size. This does not mean that half and whole are always identical. It means that the usual idea of size must be adjusted for infinite sets. Mathematicians compare these collections by asking whether each member of one can be matched with exactly one member of the other. If such a pairing is possible, the sets are considered equal in size, even when one appears to be only part of the other. The surprising behavior continues. The positive whole numbers can also be paired with all whole numbers, including negative values and zero. At first, the larger collection seems as though it must contain roughly twice as many members, plus one in the middle. A careful ordering can still list every member without missing any. Start with 0, then move to 1, then -1, then 2, then -2, continuing outward in both directions. Every whole number eventually appears somewhere in the list. The collection extending endlessly in two directions has the same type of infinity as the collection extending endlessly in one. Fractions create an even stranger result. Between any two whole numbers, there are endlessly many fractions. Between 0 and 1 alone, there is 1/2, 1/3, 2/3, 1/4, 3/4, and an unlimited supply of further values. It may seem obvious that all fractions must form a larger infinity than the whole numbers. However, the fractions can be organized in a sequence so that every possible fraction eventually receives a place. Some entries repeat the same value in different forms and can be skipped, but the complete collection remains listable. In mathematical language, this is a countable infinity, not because anyone can finish counting it, but because its members can be placed into a sequence indexed by the positive whole numbers. At this point, it may seem that all infinite collections are secretly the same size. That would at least restore some order. Mathematics refuses to be quite so accommodating. The real numbers, which include every possible point along a continuous line, form a larger kind of infinity. Even the real numbers between 0 and 1 cannot be placed into a complete list. The reason can be shown through an argument that constructs a number missing from any proposed list. Suppose someone claims to have listed every decimal value between 0 and 1. We inspect the first digit of the first entry, the second digit of the second entry, the third digit of the third entry, and continue along the diagonal. We then build a new decimal by changing each inspected digit. The new number differs from the first listed number in its first digit, from the second in its second digit, from the third in its third digit, and so on. It therefore cannot match any entry on the list. No matter how the list was arranged, another real number remains outside it. This shows that one infinity can be strictly larger than another. The infinity of points along a line is larger than the infinity of whole numbers. Both collections have no end, yet they cannot be matched member by member. This is one of the most important results in the study of infinity because it destroys the idea that infinity is one vague quantity beyond counting. There are different sizes of infinity, and once the door is opened, mathematics finds an endless hierarchy rather than a single final level. For any collection, we can consider the set of all possible selections from it. This new collection is always larger than the original, even when the original is already infinite. Starting with the whole numbers gives one larger infinity. Repeating the process produces another, then another, without arriving at a greatest possible size. Every attempt to define the largest infinity can be exceeded by constructing a still larger collection from it. This has a direct effect on the idea of every possible universe. Suppose each logically consistent universe can be described by a finite text, a computer program, or an ordered list of rules. Those descriptions would form a countable collection because every finite string made from a finite alphabet can be arranged in a sequence. Yet some mathematical structures may require more information than any finite description can hold. If physical existence is identified with every mathematical structure, the total collection may be far larger than any simple library of written laws. The difficulty grows because not every description identifies one clear object, and not every mathematical structure can be specified in a compact way. Some contain information that cannot be compressed into a shorter rule. A universe might be simple to describe at a fundamental level while producing extremely complicated behavior, or it might require an enormous amount of information merely to state its initial condition. The phrase "every possible universe" therefore depends on what counts as possible, what counts as distinct, and what kind of description is allowed. Logical consistency seems like a natural boundary, but even logic is not as simple as it first appears. A formal system begins with rules and basic assumptions, then allows conclusions to be derived from them. For powerful enough systems, there can be true statements that cannot be proven using the rules available inside that system. This does not mean logic has failed. It means a system may be unable to confirm every truth about its own structure. There are also limits on what can be decided by a universal method. No single procedure can correctly determine in every case whether any possible computer program will eventually stop or continue forever. Some problems cannot be solved by building a faster machine or waiting longer. The limitation is built into the logical structure of computation. These results matter when we imagine a final observer surveying all possible realities. Such an observer would need to identify every consistent system, determine which descriptions refer to the same structure, and decide every relevant fact about each one. Mathematics suggests that no ordinary mechanical procedure can complete that task. The collection may be too large to list, and the properties of its members may not all be decidable from within one universal framework. The edge of existence may therefore be an edge of description rather than a distant boundary. There may be no final wall beyond which nothing exists. Instead, there may be a point where our questions stop having one clear meaning. Asking what lies outside every possible reality assumes that outside remains a valid relation. If the collection already includes every space, every time, every law, and every consistent framework, then an outside location would itself need to belong to some further structure. The question recreates the very thing it tries to move beyond. This resembles asking what happened before time began. The word before already assumes an ordering in time. If time itself has a boundary, ordinary temporal language may no longer apply beyond it. In the same way, asking what exists beyond all existence assumes a larger domain in which the included and excluded things can be compared. The question may be grammatically correct while failing to identify a coherent situation. Infinity also complicates physical reality. Space may be infinite, finite, or finite without having an edge. The observable universe is finite because light has travelled for a limited time and can reach us only from a limited region. This does not tell us whether the entire universe is finite. Space may continue far beyond what we can observe, perhaps without end. An infinite universe would not necessarily contain every imaginable arrangement. That depends on how matter is distributed, whether regions are sufficiently varied, and whether there are limits on the number of possible states within a region. If space extends endlessly and suitable conditions repeat, then distant regions might resemble our own closely. Some popular discussions suggest that there could be exact copies of Earth or versions of every possible history at enormous distances. Such claims depend on assumptions that are not established simply by saying that space is infinite. An endless collection does not automatically contain every possibility. The sequence of positive whole numbers is infinite, yet it never contains a fraction. A line can extend forever in one direction without visiting any point away from that line. Infinity provides unlimited continuation within a structure, but it does not guarantee that the structure contains every type of thing. Time could also continue without end, though this would not make every event inevitable. A stable system may repeat decay, approach equilibrium, or continue changing without visiting every possible state. The physical future of our universe depends on dark energy, matter, gravity, quantum behavior, and processes that remain partly uncertain. Infinity is not a substitute for a physical model. Black holes introduce another connection. Their interiors push current theories toward regimes where gravity and quantum mechanics must be combined. Some quantities appear unbounded in classical descriptions, but physicists generally treat this as evidence that the theory is incomplete, rather than proof that literal physical infinities exist. Nature may contain processes that our present equations describe with infinite values, because the equations have been extended beyond the range where they apply. This is similar to a map that becomes unreliable near an uncharted region. A line running off the edge of the paper does not prove the road continues in exactly the same way forever. It tells us the map has stopped providing information. Physical infinities may sometimes reveal deep features of reality, but they may also signal the need for a better description. The beginning of the universe presents the same issue. Tracing cosmic expansion backward with general relativity leads toward conditions of extreme density and temperature. A simple account may describe an initial singularity, but a full theory of quantum gravity could replace that picture with a different structure. The universe may have emerged from an earlier phase, a bounce, a quantum state, or something not adequately described by ordinary time. These remain open possibilities rather than settled conclusions. Infinity inside mathematics is precise and unavoidable. Infinity in physics requires evidence and interpretation. A mathematical line contains infinitely many points. A physical ruler may not be divisible into independently meaningful regions without limit. Quantum theories and gravity suggest that our ordinary ideas of distance may change at extremely small scales, but no complete tested theory has yet given a final answer. The human mind encounters infinity through finite experience. You cannot see an endless line in full. You see a segment and understand the rule that allows it to continue. You cannot count every whole number. You grasp that no final one exists. You cannot inspect all points along a continuous interval. Mathematics proves properties of the collection without displaying every member individually. This is an important ability. Human thought can reason about structures far larger than anything a person could physically examine. A short definition can refer to an infinite collection. A finite proof can establish something about every member. The mind does not hold infinity as a complete image. It handles it through rules, relationships, and logical consequences. A hypothetical higher dimensional being would face a similar limit if the hierarchy of infinities has no greatest member. No matter how broad its viewpoint, a larger collection could be defined. The being might see all histories within one universe, all universes within one theory, or all structures of a certain type, yet the word all would continue to require a boundary. Once the boundary is specified, mathematics can ask about the collection of every possible subset, producing something larger. This prevents the staircase from ending in a final platform called infinity. There is no largest ordinary number and no largest infinite size within standard set theory. The idea of going beyond the seventh dimension, therefore, does not lead to one final realm containing everything in a simple box. It leads to a hierarchy in which every completed totality can be examined from a broader level. At first, this may seem to make the entire journey pointless. If no final view exists, perhaps nothing has been explained. The opposite is true. Each level has shown precisely how a viewpoint becomes limited. The point could not imagine the line could not move across the plane could not access depth. We cannot step through a fourth spatial direction or view an entire higher structure directly. A being that surveyed many universes might still face mathematical collections beyond its own framework. There may be no position from which everything is equally available. Knowledge may always depend on structure, access, and the rules connecting an observer to what can be observed. Even an infinite reality does not imply an infinite observer. A mind must receive, store, and compare information. Those activities require organization and limits. A being containing literally unlimited detail would be difficult to distinguish from the total reality it was meant to observe. This changes the idea of existence itself. At the lower levels, existence meant occupying a position. A point existed at one location. A line contained positions. A body occupied a volume. Space-time extended existence through a history. Branching timelines treated one history as one option. Collections of universes allowed different laws. At the level of every consistent structure, existence became almost identical to logical possibility. Beyond that, the question is no longer only what exists, it becomes what we mean by existence. Does a mathematical object exist in the same way as a chair? Does a possible universe exist if no observer within our universe can interact with it? Does a future possibility exist before it is experienced? Does a branch count as real when it can never communicate with another branch? There is no single accepted answer. A chair exists physically because it interacts with matter, reflects light, supports weight, and becomes unusually noisy when moved at night. A mathematical triangle exists as an abstract structure, though no physical drawing is perfect. A fictional city exists as information within stories, but not as a physical location available for travel. Different uses of the word existence refer to different kinds of reality. The dimensional ladder gradually blurred these categories. Geometric dimensions were abstract structures used to describe physical space. Space-time became part of tested physics. Higher collections moved into speculation and philosophy. Infinity now forces us to keep asking which type of existence is intended. A logically consistent universe may be possible without being physically realized. A physical theory may allow several solutions while only one describes our cosmos. A mathematical structure may exist abstractly without containing observers. A story may describe a coherent world without that world existing beyond the minds and materials carrying the story. Treating all these forms as identical, is a philosophical choice rather than an experimental discovery. There is still a practical centre to all of this. Whatever reality may contain beyond our observations, you experience one life through one sequence of moments. Your body occupies three-dimensional space. Your history extends through time. Decisions affect the route ahead, whether the alternatives exist physically or only as unrealized possibilities. The laws of this universe shape everything you can touch, measure, remember, and become. The existence of larger structures would not make the local world less real. A page remains meaningful even when it belongs to a book. A city remains real even though it occupies a small region of a planet. A moment remains important even if time extends far beyond it. Scale does not remove significance. This is easy to forget when discussing infinity. The largest possible collection can make an individual life seem negligible, but size and value are not the same. One conversation can matter to the people involved even if the universe contains countless stars. A decision can change a life even if alternative histories are imaginable. The fact that a human body occupies a tiny region of space-time does not make its experiences unreal. Infinity changes comparison more than it changes meaning. A finite life does not compete with the age of the universe. A person does not need to be large in space or long in duration to be important within the network of events they influence. Every action occurs locally, and local events are how physical histories are built. The journey began with a point that had nowhere to go. Giving it one direction created a line. Adding another created a plane, and another created the space around you. Including time turned the present body into part of a complete history. Considering alternatives expanded one history into many possibilities. Changing the underlying conditions produced different kinds of universes. Extending the idea toward every consistent reality brought us to infinity, where no final collection can be assumed merely because language has called it complete. The staircase beyond reality has not delivered a view from outside everything, because such a viewpoint may not be coherent. It has shown how each level changes the meaning of the one below it. A point becomes a location within a line becomes an edge within a plane becomes a surface within a solid, a body becomes a section of a life becomes one path among alternatives, a universe becomes one structure among possible structures. Infinity prevents the final collection from becoming simple. After travelling this far, the room around you remains exactly where it was. The walls still meet at familiar angles. The floor continues to perform the useful task of stopping nearby objects from falling toward the centre of Earth. Your clock continues to mark time in the ordinary way, and the next morning will probably contain tasks that pay little attention to the possibility of larger infinities. Yet the familiar room can now be understood differently. Every point within it marks a location. Every edge extends along a line. Every surface occupies a plane. Every object fills a volume. Every movement becomes part of a history through space-time. Every decision opens questions about alternatives, and every physical law belongs to a universe that may or may not be the only possible kind. That does not require us to imagine hidden visitors beside the bed or alternative versions of the kettle making tea under different laws of physics. The purpose is not to replace ordinary reality with speculation. It is to see how much structure is contained inside the ordinary things we usually ignore. Where are you listening from now, and how much time has passed since we began? Your location has probably changed little, but your position in time has moved forward through every sentence. The version of you who heard the opening greeting belongs to an earlier section of your history. The version listening now carries a memory of the route between them. If this long journey through dimensions has helped you relax, think, or simply remain curious for a while, you may like the video, subscribe to Physics with William, and share it with someone who enjoys exploring difficult questions without needing every question to have a final answer. Science often advances by finding clearer limits, better definitions, and more useful ways to ask what comes next. For tonight, there is no need to solve infinity or decide whether every possible universe exists. It is enough to understand that reality changes with the viewpoint used to describe it, that higher structures can contain lower ones without making them false, and that the word everything may be far more complicated than it first appears. The point, the line, the plane, the body, the lifetime, the branching histories, and the possible universes have all led back to the same practical fact. You are here within one location, one moment, and one experienced reality. Whatever may exist beyond it, this is the part available to you now, and it is large enough to contain a quiet room, a listening mind, and one final stretch of time before sleep.